What if the universe is not just a vast expanse of stars, but a realm filled with unimaginable mysteries waiting to be uncovered? From the enigmatic whispers of black holes to the terrifying allure of rogue planets, the cosmos is brimming with phenomena that challenge our understanding of reality. Join us as we delve deep into the ocean of strange theories surrounding cosmic structures, where gravitational forces warp the fabric of space itself and bizarre objects lurk beyond our sight. Black holes are regions in space where gravity has pulled so strongly that nothing, not even light, can escape from them. This powerful gravitational pull occurs because a substantial amount of mass is compressed into a very small area. Imagine squeezing the weight of an entire star into a single point. This intense concentration of mass warps the fabric of space and time around it. What makes black holes particularly fascinating, and indeed terrifying, is the way they challenge our understanding of the universe. When objects venture too close to a black hole, they are unable to return. The boundary surrounding a black hole is known as the event horizon. Crossing this invisible line means you can never escape. It's a point of no return. Any light or matter that crosses this boundary appears to vanish from our observable universe, creating an eerie aura of mystery. Additionally, the size and type of black hole can vary dramatically. Stellar black holes arise from collapsing massive stars, while supermassive black holes, found at the centers of galaxies, contain the mass equivalent of millions to billions of suns. The sheer scale and power of these gigantic entities can lead to violent interactions with nearby stars and gas clouds, producing brilliant bursts of radiation visible across vast distances. This combination of inescapability, immense gravity, and the potential for destructive force captures our imagination and instills a sense of dread, making black holes some of the most enigmatic and fearsome phenomena in the cosmos. They represent the limits of our knowledge, the extremes of physical laws, and a terrifying reminder of the vast, often hostile forces that shape our universe. Neutron stars are born from the remnants of massive stars after they go through a spectacular death known as a supernova. When a star that is at least 8 times the mass of the Sun exhausts its fuel, it can no longer support itself against the pressure caused by gravitational collapse. The outer layers of the star explode outward, while the core contracts under its own gravity. During this collapse, protons and electrons combine to form neutrons, resulting in a densely packed core composed almost entirely of these subatomic particles. This transformation is key to the formation of a neutron star, as it occurs in a matter of seconds. The result is an incredibly small and extraordinarily dense object. To put it simply, a neutron star can contain more mass than the Sun, but is collapsed into a sphere roughly the size of a city, packing the mass of an entire star into a volume that is incredibly compact. The incredible density of a neutron star comes from the strong nuclear forces that hold neutrons together. Imagine compressing material to such an extreme that the space between its atoms gets eliminated. That's what happens in neutron stars. 1 teaspoon of neutron star material could weigh as much as an entire mountain on Earth. Besides their density, neutron stars also possess incredibly strong gravitational forces. This immense gravity can warp space and time around the star. Additionally, many neutron stars spin at incredible rates, sometimes making hundreds of rotations per minute, and emit beams of radiation from their magnetic poles. As these beams sweep across the universe, they can be detected as pulsars, pulsating sources of radiation that mark the rotation of the neutron star. Thus, the fascinating journey from a massive star to the creation of a neutron star showcases the extraordinary forces of nature and their capability to create unimaginable densities and power. Pulsars are highly magnetized, rotating neutron stars that emit beams of radiation, typically in the form of radio waves. They are remnants of massive stars that have exploded in supernova events, leaving behind cores that are incredibly dense, so dense that a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. As these neutron stars spin, they project their beams of radiation out into space, much like a lighthouse sweeping its light across the horizon. If one of these beams happens to point towards Earth, we observe repeated signals, like ticking clockwork, leading to the nickname pulsar. What fascinates scientists is not just their existence, but the extreme conditions under which they operate. Pulsars rotate at astonishing speeds, some completing a rotation in just a few milliseconds, leading to a gravitational environment that pushes the boundaries of our understanding of physics. The intense gravity around a pulsar causes space and time to warp significantly, and this intricate interplay becomes a testing ground for theories like general relativity. Furthermore, pulsars possess strong magnetic fields that are billions of times greater than Earth's magnetic field. This combination of fast rotation and strong magnetism produces complex phenomena like glitches, where the pulsar's timing suddenly shifts. Such glitches challenge our current models of stellar physics, as they suggest that the interiors of these stars might be behaving in ways we do not fully comprehend. Observing pulsars helps physicists investigate fundamental questions about the nature of matter, gravity, and even the behavior of space-time under extreme conditions, revealing that the universe still holds many secrets waiting to be uncovered. A magnetar is a unique type of neutron star, formed from the remnants of a supernova explosion. What sets magnetars apart is their extraordinarily powerful magnetic field, which can be 1,000 times stronger than that of typical neutron stars and even trillions of times greater than Earth's magnetic field. Imagine a magnetic force so intense that it can affect the very fabric of space around it. The energy generated by a magnetar's magnetic field is not just impressive, it has profound implications. This intense magnetism causes the star's surface and even its immediate surroundings to be bombarded with high-energy radiation, particularly in the form of X-rays and gamma rays. Think of it as a cosmic lighthouse, sending out pulses of energy that can be detected from vast distances. The magnetic field also distorts space. It influences the motion of charged particles in its vicinity, steering them along magnetic field lines and creating jets of high-energy particles that shoot out into space. This process can disrupt nearby celestial bodies, altering their own magnetic environments and causing phenomena such as auroras on planets that find themselves in close proximity. Moreover, the immense gravity of a magnetar, combined with its magnetic forces, can lead to catastrophic effects on surrounding matter, from pulling in material from companion stars to influencing the dynamics of nearby gas clouds. The interplay between its magnetic field and surrounding space transforms these stars into some of the most fascinating and extreme laboratories of physics in the universe. White holes are fascinating theoretical constructs that offer a stark contrast to black holes. While black holes are regions in space where gravity is so powerful that nothing can escape from them, white holes are imagined as entities that expel matter and energy, almost as if they were the opposite side of the coin. To understand this better, picture a black hole as a funnel leading into a dark abyss. Once something crosses the threshold, known as the event horizon, it cannot return. On the other hand, envision a white hole as a fountain. It allows material to flow out, but blocks anything from entering. While black holes trap everything that ventures too close, white holes theoretically serve as the ultimate means of release. The key distinction lies in their behavior regarding time and matter. A black hole attracts and consumes, pulling objects into an irreversible path toward infinite density at the singularity. For white holes, the laws of physics as we currently understand them would suggest that they are non-physical realities where the conservation of mass and energy could allow matter to emerge from them, but nothing could ever fall in. This cup of cosmic wonder, however, comes with complexities. White holes have not been observed in the universe, and their existence is purely hypothetical. Some theories speculate that white holes could be connected to black holes through a wormhole, creating a bridge between two vastly different regions of space and time. While black holes are known for their enigmatic pull and voracious consumption, white holes inspire thoughts of vibrant ejections of cosmic materials. These ideas encourage deeper exploration into the fundamental laws of physics and the mysteries of our universe, even if they remain, for now, more theoretical than tangible. Rogue planets are intriguing celestial bodies that drift through the cosmos unattached to any star system. These planets are often formed in the same way as regular planets, coalescing from gas and dust in a protoplanetary disk. However, during their development, they can be ejected from their parental systems due to gravitational interactions with other massive objects, such as neighboring planets or passing stars. What sets rogue planets apart is their isolation. Unlike typical planets that orbit stars and derive energy and warmth from them, rogue planets wander in the dark expanses of space, relying on residual heat from their formation or internal processes. This challenging living condition leads scientists to ponder what kind of environments might exist on these lonely worlds. The anomaly of rogue planets lies not only in their solitary nature, but also in their abundance, which may rival or surpass that of stars in our galaxy. Their existence challenges our understanding of planetary formation and stability. Most planetary models are based on the idea that planets form close to their stars, so rogue planets represent a significant deviation from this norm. The exploration of rogue planets opens exciting avenues for research, including the possibility of life in extreme conditions. While these planets might seem barren and inhospitable, the mysteries they hold about planetary systems and their dynamics offer a fresh perspective on the complex tapestry of our universe. Supermassive black holes hold a critical position at the centers of galaxies, wielding immense gravitational power that profoundly influences their surroundings. Picture a heavy anchor at the center of a swirling galaxy. This anchor not only holds it together, but also shapes its very structure and behavior. The gravitational pull of these colossal entities affects the motion of stars and gas clouds, guiding their paths and maintaining the galactic order. As supermassive black holes consume matter, they can unleash vast amounts of energy, particularly when matter spirals around them in what is known as an accretion disk. This process can heat up surrounding gas and dust to incredibly high temperatures, causing it to emit bright radiation. This intense energy output can feed back into the galaxy, influencing star formation. In some cases, the energy released may suppress the birth of new stars by heating up gas that would otherwise cool and condense into stellar nurseries. Furthermore, supermassive black holes can drive powerful jets of particles that shoot outwards at nearly the speed of light. These jets can extend far beyond the galaxy itself, impacting the intergalactic medium and even affecting neighboring galaxies. As the jets interact with surrounding gas, they can trigger shock waves, compressing material and potentially sparking new star formation regions in their wake. Supermassive black holes significantly shape their host galaxies. They create a dynamic interplay of forces, balancing gravity and energy, fostering environments that can either promote or inhibit the formation of stars, while simultaneously restructuring the galaxy's architecture over time. This fascinating relationship underscores the role of black holes not just as cosmic vacuum cleaners, but as integral players in the galaxy's life cycle. Quasars, or quasi-stellar objects, are among the most astonishing phenomena in the cosmos. To understand them, we first need to explore their connection to supermassive black holes, which can be found at the centers of many galaxies. Quasars are essentially the incredibly bright cores of these distant galaxies, powered by material falling into the black hole. Imagine a cosmic furnace, fueled by gas and dust, spiraling toward the black hole. As this material gets consumed, it forms an accretion disk, a swirling mass that heats up to extreme temperatures due to friction and gravitational forces. This process releases a tremendous amount of energy, often outshining entire galaxies. In fact, the light emitted from quasars can be billions of times more intense than our own sun. The sheer brightness of a quasar comes from its vast distance from Earth. As light travels across the universe, it can be stretched and dimmed, making these objects appear incredibly luminous in comparison to nearby stars. This allows us to observe quasars at enormous distances, effectively enabling us to glimpse the universe as it was billions of years ago. Moreover, quasars emit energy not only in the form of visible light, but also across the entire electromagnetic spectrum, including radio waves, ultraviolet light, and X-rays. Moreover, quasars emit energy not only in the form of visible light, but also across the entire electromagnetic spectrum, including radio waves, ultraviolet light, and X-rays. This phenomenon makes them powerful beacons in the universe, captivating astronomers and providing insight into the formation and evolution of galaxies. Essentially, they serve as a window into the distant past, revealing the conditions that shaped the universe we see today. Cosmic strings introduce a fascinating complexity to our understanding of space-time. These theoretical structures can be envisioned as incredibly thin, one-dimensional filaments that stretch across the cosmos. Imagine them as the seams on a piece of fabric, but instead of merely holding material together, they fundamentally alter the fabric of space-time itself. When cosmic strings form, they do so during the early moments of the universe, a time when conditions were extreme and chaotic. As the universe cooled and expanded, certain areas underwent phase transitions, leading to the creation of these strings. They are predicted to possess immense density, and their gravitational influence is so strong that they can warp the surrounding space-time, much like a heavy bowling ball placed on a stretched rubber sheet. The presence of these cosmic strings challenges our traditional concepts of space-time in several ways. For one, they can create distinctive gravitational effects, causing light to bend around them, resulting in what we call gravitational lensing. This means that the path of light is not just determined by distance and mass, but can be heavily influenced by the existence of these strings. In their vicinity, space-time itself can behave in unexpected ways. The warping caused by cosmic strings can lead to phenomena like the creation of closed time-like curves. These are paths through space-time that might allow for time travel, raising questions about causality and the nature of time itself. Such implications can stretch our understanding of what it means to exist in a consistent universe. Moreover, cosmic strings could be connected to the theories that aim to unify different forces of nature, like gravity and electromagnetism. As researchers continue to investigate these structures, they could provide insights into the very fabric of reality, moving us closer to a deeper understanding of the universe's origins and its fundamental laws. Cosmic strings not only captivate the imagination, but also serve as a reminder of how much remains to be uncovered in the mysterious interplay of space, time, and reality. Galaxies are magnificent structures that form from the gradual accumulation of gas, dust, and dark matter over billions of years. In the early universe, tiny fluctuations in density interrupted an otherwise smooth distribution of matter. These areas of higher density began to attract more matter due to gravity, creating clumps. Over immense stretches of time, these clumps grew larger, merging together and forming the first stars. As these stars burned bright and lived out their lives, they expelled heavy elements into the surrounding gas, enriching it and allowing for the birth of new stars and planets. As galaxies evolve, they exhibit both beauty and terror in their myriad features. One particularly unsettling aspect is the presence of supermassive black holes at their centers. These black holes can contain millions or even billions of times the mass of our Sun, exerting a gravitational pull that could trap anything that ventures too close. The intense forces near these black holes can create accretion disks of gas and dust that spiral in, heating up and releasing powerful streams of radiation, making these regions some of the brightest and most dangerous spots in the universe. Another frightening feature is the phenomenon known as galactic cannibalism. Larger galaxies can attract and absorb smaller ones, merging their stars, gas, and dark matter while potentially disrupting existing star systems. This process can lead to violent interactions that alter the structure of both galaxies, potentially triggering new waves of star formation, but also creating chaos and instability in the cosmic neighborhood. And then there are galaxy clusters, vast assemblages of galaxies bound together by gravity. These clusters can harbor dark matter halos, which are invisible but exert immense gravitational influence. The environment within these clusters can often be hostile, with interactions among galaxies leading to disruption and dissolution of star systems, and leading to the formation of colossal jets and outflows as galaxies grapple with one another. In this unfolding cosmic drama, the story of galaxy formation combines the beauty of creation with the stark realities of survival and dominance in the universe. The landscape of galaxies is as awe-inspiring as it is daunting, a vivid reminder of the forces at play across vast expanse of space. The Great Attractor is a mysterious region of space that exerts a powerful gravitational pull on galaxies within our cosmic neighborhood. Imagine this area as an enormous mass hidden behind the Milky Way, which draws in neighboring galaxies, creating a kind of cosmic traffic jam. Although we can observe the effects of its gravity, pinpointing its exact nature and structure has been challenging. Astronomers have determined that the Great Attractor lies in the direction of the southern hemisphere, nestled within the Centaurus and Hydra constellations. This region is a hub of galactic activity, housing dense clusters of galaxies that contribute to its gravitational strength. The intrigue arises from our inability to study it directly. The Milky Way's dust and gas obscure our view, making it difficult to see what's causing this gravitational attraction. What's baffling to researchers is not just the invisible force at work, but its scale and the nature of its mass. Estimates suggest that the Great Attractor is part of a much larger structure known as the Laniakea supercluster, which contains vast filaments of galaxies and dark matter that weave through the universe. As we delve deeper into this enigma, it raises profound questions about the distribution of mass in the universe and how these colossal structures influence the cosmic ballet of galaxies. The more we uncover, the more we realize that the universe holds secrets that continue to challenge our understanding of gravity and cosmology. Understanding the dynamics of galactic collisions is a complex yet fascinating pursuit that challenges the limits of our knowledge. At their core, galactic collisions occur when two galaxies approach each other due to their mutual gravitational attraction. Over millions of years, these colossal entities, containing billions of stars, gas, dust, and dark matter, can alter dramatically as they interact. Initially, as two galaxies draw near, their gravitational fields begin to influence not just their stars, but also their gas and dust. This interaction creates stunning visual phenomena, such as beautiful tidal tails, long streams of stars and gas that extend outwards like cosmic ribbons. As they merge, the gravitational forces can induce immense pressures that compress gas clouds, triggering waves of star formation. This can lead to the sudden birth of new stars in what is referred to as a starburst event, illuminating the galaxies in bright light. However, it's not simply a case of two galaxies merging seamlessly. The gravitational turmoil leads to significant structural changes, often resulting in the formation of an entirely new galaxy. The central regions may spiral into each other, forming a larger supermassive black hole that could reside at the heart of this new entity. While cosmologists have made great strides in modeling these events using simulations and observations, fully grasping every aspect of galactic collisions remains elusive. Factors such as dark matter's role, the precise dynamics of stellar interactions, and the complex behaviors of the gas involved add layers of intricacy that researchers are still unraveling. The aftermath of these cosmic clashes also includes possible disruptions to planetary systems and existing habitats, raising questions about their long-term stability. Galactic collisions are chaotic yet orderly, beautiful yet devastating, illustrating the dynamic nature of our universe. As technologies advance and our observational capabilities improve, we inch closer to a comprehensive understanding of these grand cosmic events, showcasing the ever-changing tapestry of the cosmos. Dark matter galaxies operate on principles that are quite different from the galaxies we see in the universe filled with stars and gas. In typical galaxies, the visible matter, like stars and planets, forms the structure we can observe. However, in dark matter galaxies, most of the mass is not made up of atoms, which means it does not emit, absorb, or reflect light, making it invisible to our telescopes. To understand how these galaxies function, it's essential to consider that dark matter acts like a scaffolding, providing the necessary gravitational influence that holds galaxies together and affects their formation. Inside these dark matter galaxies, the gravitational clumping of this unseen matter is responsible for the motion of stars. Even though we cannot see the dark matter itself, we can detect its effects indirectly. For instance, astronomers observe the speeds at which stars orbit within a galaxy. These speeds suggest there is far more mass present than what we can see, indicating the presence of dark matter. Detecting dark matter is a significant challenge because it does not interact with electromagnetic forces, which means it doesn't create light waves that we can perceive. This lack of interaction keeps dark matter hidden from direct observation, making it elusive to current technologies. Scientists employ various observational techniques, such as looking for the gravitational influence of dark matter on nearby galaxies or studying the cosmic microwave background radiation for clues about its presence and distribution. Moreover, dark matter's nature implies that it also does not coalesce into structures like ordinary matter does. This property allows dark matter to exist in a more diffuse state, unlike the dense clusters formed by visible matter. As a result, while dark matter galaxies intriguingly shape the cosmos and facilitate galaxy formation, their detection remains a head-scratching mystery wrapped in the enigma of our universe's architecture. Galactic superclusters are enormous structures in the universe that encompass groups of galaxies, galaxy clusters, and even smaller groups of galaxies. To visualize a supercluster, imagine a vast congregation of stars, gas, and dark matter, all bound together by gravity. They represent some of the largest known structures in the cosmos, formed through the gravitational attraction of matter over billions of years. When considering their scale, superclusters stretch across distances that are nearly unimaginable. A supercluster can span hundreds of millions of light-years, which means that light traveling from one edge of the supercluster to the other would take hundreds of millions of years to traverse. To put that into perspective, a light-year, the distance light travels in a single year, is already a staggering measure. But when discussing superclusters, we are talking about immense expanses where vast groups of galaxies are in motion, often towards one another. One prominent example is the Laniakea supercluster, which contains our own Milky Way galaxy and stretches across about 100 million light-years. Within Laniakea, galaxies are pulled together by gravitational interactions, creating a complex web of structures that forms the backbone of the universe's large-scale organization. In the grand context of the universe, superclusters represent only a fraction of the vastness we see. The universe itself is filled with countless superclusters, along with vast empty regions called voids. The interplay between these structures shapes the universe's overall architecture, demonstrating how galaxies and clusters evolve in response to the forces of gravity over time. In this way, superclusters are vital to understanding not only the cosmos around us, but also the very fabric of the universe itself. The structure of the universe, when examined on the largest scales, reveals a cosmos that often surprises and challenges our understanding. To envision this, consider the universe as an intricate tapestry woven from galaxies, clusters, and vast voids. Initially, one might expect these elements to be evenly distributed, much like grains of sand spread uniformly across a beach. However, what scientists have discovered is much more complex. Instead of a neat arrangement, galaxies tend to cluster together in massive formations known as galaxy clusters. which themselves are part of even larger structures called superclusters. These celestial groupings create a web-like structure where threads of visible matter stretch across enormous distances, leaving behind vast empty spaces or voids that are astonishingly devoid of galaxies. This is akin to a cosmic network of filaments, where some areas are densely populated while others are eerily empty. Additionally, the presence of dark matter plays a crucial role in shaping the universe's structure. Although it cannot be directly observed, dark matter's gravitational influence is essential in forming these large-scale structures. It acts as an invisible scaffolding, guiding the formation of galaxies and clusters. The implications of this dark matter are profound, suggesting that the bulk of matter in the universe is shrouded in mystery, altering our understanding of the composition of everything we see. Moreover, the universe is not static. It is expanding, with galaxies moving away from one another. This expansion adds another layer of complexity as it affects how structures evolve over time. The realization that the rate of this expansion is accelerating, driven by a mysterious force known as dark energy, further defies our basic expectations of a stable universe. The universe's grand-scale structure defies simple patterns. It is marked by a complex interconnectivity, dark matter's unseen influence, and an expanding nature, all of which reshape our understanding of the cosmos in ways that are continuously evolving and challenging our expectations. Dark energy is a mysterious force that permeates the universe, playing a crucial role in its expansion. Imagine the universe as a balloon that is being blown up. As more air fills the balloon, it stretches, and so does the space between every point on its surface. In a similar way, the universe is expanding. But what's driving this expansion at an accelerating rate? That's where dark energy comes into play. Scientifically speaking, dark energy is thought to make up a significant portion of the universe, potentially around 70%. It appears to act as a sort of anti-gravity, opposing the gravitational pull that pulls matter together. While gravity works to slow down the expansion by drawing galaxies and other celestial objects closer together, dark energy seems to push them apart. This opposition is what causes the rate of expansion to speed up over time instead of slowing down as one might expect due to gravity. The exact nature of dark energy remains one of the greatest mysteries in cosmology. Observations show that the rate of expansion is increasing, a discovery that has profound implications for our understanding of the universe. Scientists have likened dark energy's effect to a constant force that affects vast distances, extending its influence far beyond what we can see. With every second that passes, galaxies are moving further away from each other, driven by this enigmatic force. Understanding dark energy could eventually lead us to answers about the fate of our universe and how it will continue to evolve over billions of years. Cosmic voids are vast, empty regions of space that stand in stark contrast to the clusters of galaxies that populate the universe. Imagine a cosmic web where many dense nodes are connected by filaments, with these voids acting like the spaces between the threads. Covering a significant portion of the universe, these voids can be millions of light-years in diameter. The existence of these voids provides intriguing insights into the composition and structure of the universe. When astronomers study them, they find that the universe is not uniformly distributed. Rather, it has an intricate layout that reveals how matter is clustered. In these empty regions, the density of matter is notably lower than the average density of the universe. This scarcity hints at a cosmic era when matter was still primarily gaseous, lacking the clumping that leads to the formation of galaxies. Moreover, voids suggest that around them, dark energy plays a crucial role. Dark energy is the mysterious force that is thought to drive the accelerated expansion of the universe. The vast emptiness of voids supports the idea that the universe is not only expanding, but also doing so at an increasing rate. Since dark energy permeates all of space, its influence is felt even in these voids. Studying cosmic voids enhances our understanding of both the formation of galaxies and the overall layout of the universe. They act as laboratories for examining the cosmic expansion and the role of dark energy, offering a window into the complex and dynamic processes that shape our universe. By analyzing the structures and behaviors within these vast emptiness, scientists piece together the cosmic puzzle that governs everything from the smallest galaxies to the largest cosmic scales. Spiral galaxies and elliptical galaxies represent two primary forms of galactic structure, each with distinct characteristics and formation histories. To understand these differences, let's first visualize what each type looks like. Spiral galaxies are often majestic, displaying a flat disk with swirling arms that radiate out from a central bulge, resembling the shape of a pinwheel. Elliptical galaxies, on the other hand, have a more rounded or oval appearance, lacking the prominent structure of spiral arms. In terms of formation, spiral galaxies tend to form in a more dynamic environment. They develop from an accumulation of gas and dust that cools and collapses under its own gravity, allowing for the formation of stars within their disk. The presence of this gas creates ongoing star formation, which is visible in the bright blue regions of the galaxy where young stars shine. These galaxies often have a mix of old and young stars, along with regions of active star formation. Elliptical galaxies, in contrast, are believed to have experienced a more tranquil evolutionary process, often formed through the merger of smaller galaxies. This merger can lead to greater gravitational interactions that disrupt the gas flow, resulting in a halt to new star formation. As a result, elliptical galaxies primarily contain older stars, giving them a yellowish or reddish appearance. The absence of significant amounts of gas means that star formation is minimal, creating a more uniform stellar population without the vibrant, active regions found in spiral galaxies. Additionally, the overall structure reflects their different histories. Spiral galaxies exhibit a flattened disk and a more organized rotation pattern, whereas elliptical galaxies have a more three-dimensional distribution of stars with varying orbital paths. This difference in structure also correlates with their mass and size. Spiral galaxies can range in size but tend to be less massive than the largest elliptical galaxies, which can be colossal structures with numerous stars packed densely. The differences between spiral and elliptical galaxies are rooted in their formation and evolutionary paths. Spiral galaxies are characterized by ongoing star formation and prominent structures, while elliptical galaxies emerge from the gradual accumulation of stars through mergers, leading to a smoother, older stellar population. Understanding these distinctions reveals the diverse processes that shape our universe, each galaxy telling a unique story of cosmic evolution. The Big Crunch theory presents a fascinating outlook on the ultimate fate of our universe. Imagine the universe expanding from an original point in a fine, dense state. The Big Crunch posits that this expansion might one day reverse. As galaxies drift apart today, gravitational forces between masses could gradually overcome the momentum of that expansion. Picture a colossal cosmic balloon that, after being inflated, starts to deflate, pulling everything back together into an incredibly hot and dense core once again. This collapse suggests a cyclical nature to the universe, where after reaching a singular state of extreme compression, it might eventually trigger another Big Bang, leading to a fresh cycle of expansion. In contrast, the notion of the Big Freeze paints a vastly different picture. According to this theory, the universe will continue expanding indefinitely. Picture a vast, dark expanse where galaxies stretch further apart as they lose the energy required for new star formation. As time unfolds, the cosmos will become increasingly cold and desolate. Stars will exhaust their nuclear fuel, leading to a universe of dying stars and black holes, ultimately fading into darkness. Without the heat and light from stars, the universe may cool to near absolute zero, creating a frozen and lifeless expanse. Thus, while the Big Crunch envisions an eventual collapse and potential rebirth of the universe, the Big Freeze highlights a gradual decline into an unchanging cold state. Both theories explore possible endings to our universe, reflecting humanity's quest to understand our place in the vast, ever-expanding cosmos. Each theory provides a unique window into the cosmos's destiny, weaving together the concepts of time, space, and existence. The concept of the multiverse suggests that our universe is just one of many, perhaps an infinite number of universes, each with its own distinct properties and laws of physics. Imagine stepping into a vast library filled with countless books, where each book tells the story of a different universe, some similar to ours, while others are wildly different. While the idea may sound like science fiction, physicists explore it through various theories. One of these is the idea of cosmic inflation, proposing that soon after the Big Bang, our universe expanded rapidly, and during this process, it could have formed bubbles of spacetime, each representing a separate universe. What is extraordinary about these universes is that they may have varying physical constants, like the strength of gravity or the charge of an electron, resulting in entirely different realities. Understanding the multiverse has profound implications for our own universe. It challenges our notions of uniqueness and suggests that various laws and conditions could lead to diverse forms of life and existence beyond what we experience. If other universes exist, it raises questions about the fundamental nature of reality. Are there regions where physical laws are completely unrecognizable to us? What does it mean for concepts like chance and necessity in our own existence? Moreover, the multiverse invites deeper philosophical reflections. If there are countless versions of ourselves across these universes, how does that affect our sense of identity and agency? The implications also reach into scientific fields such as cosmology and fundamental physics, pushing researchers to explore, although possibly beyond direct observation. Ultimately, while the multiverse suggests a richer tapestry of reality, it remains at the frontier of theoretical physics. Our tools for exploring these ideas may still be limited, but they spark our imagination, challenging us to think beyond the boundaries of what we consider the universe. The theory of cosmic inflation provides a fascinating explanation for the very early moments of the universe, suggesting that it underwent an incredibly rapid expansion. Imagine the universe as a small balloon that began to inflate, but not just slowly. This balloon swelled exponentially, expanding faster than the speed of light for a short period. This expansion occurred within a fraction of a second after the Big Bang, a moment when the universe was extremely hot and dense. During inflation, the universe expanded so quickly that tiny quantum fluctuations, minuscule variations in energy, were stretched across vast distances. These fluctuations are essential because they laid the groundwork for the large-scale structure of the universe we observe today, such as galaxies and galaxy clusters. Without this inflationary phase, our universe would appear very different, possibly lacking the vastness and the clustered formations we see now. Furthermore, cosmic inflation addresses several critical questions about the universe's uniformity. Despite being vast, the universe has regions that share nearly identical properties even when they are light years apart. The theory suggests that those areas were once close together before being propelled away from each other during inflation. This rapid growth explains why the universe appears homogeneous, as parts that are now far apart began as a densely packed region. In conclusion, cosmic inflation not only gives us insight into the conditions right after the Big Bang, but also helps us understand the architecture of the universe around us, bridging gaps in our knowledge and offering a cohesive narrative about the birth and evolution of cosmic structures. The concept of wormholes captivates both scientists and science fiction enthusiasts by painting a picture of extraordinary possibilities that challenge our understanding of the universe. A wormhole is theorized as a tunnel-like structure linking distant points in space and time, suggesting a means to traverse immense distances almost instantaneously. This prospect opens the door to a multitude of fascinating questions about the nature of reality and our place within it. For scientists, wormholes represent an intriguing area of theoretical research that stems from the principles of Einstein's general relativity. They invoke curiosity about the fabric of space-time, pushing boundaries on what we know about gravity and the cosmos. The mathematical equations that describe these phenomena hint at the existence of shortcuts through spacetime, sparking theoretical explorations about their properties, potential stability, and how they could fit within the known laws of physics. On the science fiction side, Wormholes inspire imaginative narratives that often feature characters embarking on grand adventures or solving critical problems by traveling far beyond conventional means. This concept allows authors to explore themes of exploration, the unknown, and sometimes even the moral implications of such technology. Stories of instant travel to far-off galaxies or alternate realities resonate with our innate desire for discovery and the experience of the extraordinary. The potential for meeting other civilizations or witnessing breathtaking cosmic events fuels our imagination further. Both realms, the scientific inquiry and the imaginative storytelling, serve to elevate the idea of wormholes beyond mere fantasy. They provoke essential conversations about the limits of human understanding and the future of space exploration. In a way, they embody mankind's relentless quest for knowledge and an unyielding desire to go boldly into the unseen frontiers of the universe. Hawking radiation is a groundbreaking concept that stems from the intersection of quantum mechanics and general relativity introduced by the physicist Stephen Hawking. To understand it, imagine a black hole as a region in space with such intense gravity that nothing, not even light, can escape from it. However, quantum theory suggests that this idealized view isn't entirely accurate. In the realm of quantum physics, empty space is not truly empty. Instead, it is teeming with fleeting particles that briefly appear and vanish. Near the event horizon, the boundary of a black hole from which nothing can escape, these quantum fluctuations can lead to peculiar occurrences. Occasionally, a particle and its antiparticle pop into existence very close to the boundary. If one of these particles falls into the black hole while its partner escapes, the escaping particle contributes a kind of radiation, which we call Hawking radiation. This process means that black holes can emit radiation over time, leading to the gradual loss of their mass. Imagine a creature losing weight as it slowly consumes itself. Hawking radiation illustrates how black holes might similarly lose substance. As a black hole emits this radiation, it gradually loses energy and mass, resulting in what scientists propose could be a long, drawn-out evaporation process. Over astronomical timescales, if a black hole continues to emit Hawking radiation without gaining more mass from outside matter, it can shrink significantly. In the final stages of this process, the black hole might evaporate entirely, releasing a burst of radiation in a spectacular finale. This notion challenges our previous understandings of these enigmatic cosmic objects and opens up fascinating discussions about the ultimate fate of black holes and the nature of the universe itself. Tachyons are intriguing theoretical particles that have drawn significant attention in the world of physics. Their fundamental characteristic is the suggestion that they move faster than light. This notion challenges the established principles of physics, particularly Einstein's theory of relativity, which states that as an object accelerates towards the speed of light, its mass effectively increases, requiring ever more energy to continue accelerating. Ultimately, reaching or exceeding the speed of light is deemed impossible for objects with mass. However, tachyons, if they indeed exist, would inherently possess imaginary mass, suggesting that they are not bound by the same constraints. Their speed would not increase with energy. Instead, the more energy they have, the slower they would travel. This contradicts our conventional understanding of speed and energy relationships. Moreover, tachyons introduce complications when considering causality, the principle that cause precedes effect. If tachyons can travel faster than light, they could potentially create scenarios where an effect might occur before its cause, leading to paradoxes that challenge our understanding of time and reality itself. While tachyons remain purely hypothetical at this point, exploring their implications helps physicists probe the fundamental limits of our knowledge about the universe. Their existence would require a re-evaluation of the very foundations of physics and the nature of space and time. In this sense, Tachyons act as a fascinating window into potential realms of physics that are still beyond our current understanding. The holographic principle presents a fascinating idea that challenges our understanding of reality. Imagine a two-dimensional surface, like a flat sheet, containing all the information needed to describe a three-dimensional space like our universe. This thought-provoking concept suggests that everything we perceive in our three-dimensional world could be a projection of this two-dimensional information encoded on a distant surface, much like a hologram. This principle emerged from the study of black holes. Scientists observed that the amount of information that can be contained within a black hole is proportional to its surface area rather than its volume. This observation led to the realization that the universe may have a similar characteristic. Rather than viewing space and time as fundamental elements, the holographic principle suggests they could arise from more basic, underlying components that exist in a different realm, essentially a lower dimensional reality. To understand how this idea applies to our universe, envision a movie projected onto a screen. The images you see are not the film itself, but rather the result of light and information interacting with the screen's surface. In the same way, our three-dimensional experiences and even time could be the result of higher dimensional data projecting into the dimensions we traverse. Thus, our perceptions of space and life might be mere reflections of deeper information, reshaping our understanding of existence and reality itself. This notion raises profound questions about the nature of the universe, leading us to ponder whether what we see and feel is the real story or just an elaborate interpretation of a more fundamental underlying reality. If true, the holographic principle invites us to reconsider not only the nature of space and time, but also our place within the cosmos. Catastrophic vacuum decay presents a daunting concept in the realm of theoretical physics. To understand it, we first need to grasp what a vacuum means in this context. In physics, a vacuum is not simply an empty space, but a state of lowest energy, meaning it has the least potential energy possible. This vacuum is stable, allowing particles and forces to exist as we perceive them. However, scientists propose that our universe might actually occupy a false vacuum state, a temporary and unstable version. Imagine this like sitting on a hill where the top is not the highest point, yet it feels secure. The true vacuum represents a lower energy state, akin to the bottom of a valley, which is more stable. If a shift occurred, transitioning from the false vacuum to the true vacuum could happen suddenly, analogous to a marble rolling down the hill and quickly arriving at a much lower position. This sudden transition would not merely affect a small area, rather, it would ripple through space at the speed of light, converting everything in its path into this lower energy state. The laws of physics as we know them could disappear, leading to a complete alteration of fundamental forces. Such a transformation would fundamentally disrupt matter, obliterating everything from atoms to larger cosmic structures. The possibility of experiencing vacuum decay raises profound questions about the stability of our universe. Although theorists calculate the odds of such an event happening are extremely low, it serves as a reminder of the delicate balance that sustains existence. Each moment we experience relies on the intricate relationships of forces and particles, all existing within this seemingly stable vacuum state. While we go about our lives, the notion that a tumultuous change could exist just beyond our current reality deepens our curiosity about the fabric of the cosmos. The idea of parallel universes suggests that there are many realities existing alongside our own, each one a different variation of the universe we inhabit. Imagine our universe as a vast tree. Each branch represents a different outcome, a distinct universe shaped by choices or events that diverge in time. In this view, there could be an infinite number of branches, meaning countless universes where every possibility plays out. Scientists explore this concept through various theories, one of the most famous being quantum mechanics. This branch of physics describes how particles behave in ways that often seem strange and unpredictable. When a particle is observed, it appears to choose a specific outcome from several possibilities, much like flipping a coin. However, some interpretations suggest that all possible outcomes actually happen, each in its own separate universe. In this scenario, when we make a choice, one version of reality unfolds while others branch off into alternate realities. Another approach comes from the idea of cosmic inflation, which posits that after the Big Bang, our universe experienced rapid expansion. During this period, it's proposed that pockets of energy could have formed separate bubbles, each cooling and evolving into distinct universes that we may never interact with. These bubble universes could have different physical laws or constants governing them, leading to starkly different realities. While captivating, the existence of parallel universes remains speculative. We lack direct evidence, making it both a tantalizing theory and a challenging scientific frontier. The coexistence of these realities with our own suggests a vast and complex multiverse, but until we find methods to observe or test these dimensions, they remain an intriguing puzzle in the quest to understand the nature of existence itself. Hot Jupiters are a class of exoplanets that resemble our own Jupiter in size and composition, but orbit exceptionally close to their stars. This proximity leads to extreme temperatures that can soar to levels much higher than what we find on Jupiter, hence the term hot. The intriguing aspect of hot Jupiters lies in their unique atmospheric conditions. Due to their close orbits, these planets experience intense stellar radiation, which can heat their atmospheres to hundreds or even thousands of degrees. As a result, they often possess thick, puffy clouds that can reflect a significant amount of light and heat. This makes their combination of gas compositions and thermal dynamics a tantalizing subject for scientists. Another captivating feature is the possibility of extreme weather patterns on these planets. With such high temperatures, gases that would typically be in solid or liquid states on Earth can exist in different forms, creating dynamic weather systems that might include powerful winds and storms. These atmospheric behaviors not only offer insights into the planetary formation and evolution, but also push the boundaries of our understanding of where life might exist beyond Earth. Moreover, the discovery of hot Jupiters challenges traditional models of planet formation and migration. Instead of forming far from their stars and migrating inward, these gas giants seem to have traveled great distances, suggesting that the dynamics of planetary systems are more complex than we once believed. By studying these celestial bodies, we enhance our comprehension of planetary systems, potentially shedding light on how diverse environments in the universe can be. Super-Earths, which are rocky planets larger than Earth but smaller than gas giants, hold tantalizing clues in our quest to understand life beyond our planet. These worlds can be found in diverse environments, often located in the habitable zone around their stars, where conditions might allow for liquid water to exist. This essential ingredient for life sparks interest among scientists, as water is a fundamental component for biological processes as we know them. The composition of super-Earths can provide insights into their atmospheric conditions and potential habitability. Many of these planets may possess thick atmospheres rich in gases, including carbon dioxide and others necessary for nurturing life. By observing the changes in light from stars as these planets transit, astronomers can analyze the chemical signatures present in their atmospheres, revealing whether they possess the building blocks required for life. Furthermore, super-Earths often have geological activity that could offer stable environments for life. This activity can create a dynamic landscape, incorporating volcanoes and tectonic movement, which are essential for recycling carbon and other nutrients. A planet with geological features could foster diverse ecosystems, contributing to a robust biological environment. Some super-Earths also showcase weather patterns and seasons due to their tilted axes, similar to Earth. This variability can create different ecological niches, potentially allowing for a variety of life forms to emerge. The study of these planets expands our understanding of where life could exist beyond our solar system and informs our searches for extraterrestrial life. By investigating super-Earths, scientists may uncover signs of habitability, or even direct evidence of biological processes, such as the presence of specific gases produced by life forms. Each discovery in this realm not only sharpens our understanding of these fascinating planets, but also brings us closer to answering the profound question of whether we are alone in the universe. Venus is often referred to as Earth's twin due to its similar size and composition, but its climate stands in stark contrast, making it one of the most hostile environments in the solar system. The first factor contributing to this extreme climate is the thick atmosphere, composed mainly of carbon dioxide, with clouds teeming with sulfuric acid. This dense atmosphere creates a potent greenhouse effect, trapping heat and raising surface temperatures to a staggering degree, hot enough to melt lead. Furthermore, the atmospheric pressure on Venus is about 90 times greater than that on Earth, equivalent to being nearly a mile beneath the ocean. This immense pressure would crush any spacecraft that dared to descend to its surface without specialized engineering. Winds on Venus can reach speeds of over 200 miles per hour in the upper atmosphere, creating turbulent weather patterns. The clouds, although high above the surface, contribute to a perpetual shroud that reflects sunlight, giving Venus its bright appearance, yet preventing any cooling effect that a normal day-night cycle would provide. Winds on Venus can reach speeds of over 200 miles per hour in the upper atmosphere, creating turbulent weather patterns. The clouds, although high above the surface, contribute to a perpetual shroud that reflects sunlight, giving Venus its bright appearance, yet preventing any cooling effect that a normal day-night cycle would provide. Additionally, the constant volcanic activity suggests that the planet has an ongoing release of heat from its interior, further exacerbating the extreme conditions. With temperatures that remain consistently high, crushing pressures, acidic clouds, and tumultuous winds, Venus presents an environment where survival, as we know it, would be virtually impossible. This combination of factors results in a climate that is not just harsh, but is a powerful reminder of how diverse planetary environments can be within our own solar neighborhood. The so-called dark side of the Moon has fascinated scientists for decades, largely because it remains shrouded in mystery and was less explored than the side facing Earth. Contrary to what the name suggests, this side receives the same amount of sunlight as the visible side. It simply doesn't face us due to the Moon's synchronous rotation, meaning it takes the same time to spin on its axis as it does to orbit our planet. This hidden hemisphere has sparked curiosity due to its unique geological features and unexplored environments. From deep craters to ancient lunar maria, the surface presents clues to the Moon's history and the broader history of our solar system. Scientists speculate that studying this side could unravel the processes that shaped not just the Moon, but also the Earth and other celestial bodies. In addition to geological intrigue, the dark side of the Moon offers a pristine environment for radio astronomy. Unlike the visible side, which is influenced by Earth's radio emissions, the far side provides a quieter background for capturing faint signals from space. This could pave the way for deeper investigations into the early universe, including the formation of galaxies, stars, and the fundamental properties of space itself. Furthermore, the challenges of exploring this region inspire advancements in technology and international collaboration. Missions to the far side require careful planning and innovative solutions to communication and navigation. As spacecraft venture to this uncharted territory, they promise to expand our understanding of lunar science and the universe, demonstrating that sometimes the greatest discoveries lie beyond what we can see. The Great Red Spot on Jupiter is one of the most fascinating storms in our solar system, known for its stunning size and longevity. This colossal storm is a massive anticyclonic system, meaning it rotates in the opposite direction of storms we typically see on Earth. To visualize it, imagine a hurricane that spans several times the diameter of Earth, swirling relentlessly in the upper atmosphere of the gigantic gas planet. The dynamics of gas giant storms, like the Great Red Spot, are largely driven by the unique atmospheric conditions of their host planets. Jupiter's atmosphere is composed mainly of hydrogen and helium, and it experiences extreme thermal dynamics due to its immense size and rapid rotation. These factors create a series of powerful wind currents and convection cells. Heat from Jupiter's interior, combined with the swift rotation, contributes to the continuous formation of storms. The persistence of the Great Red Spot for centuries can be attributed to several key factors. First, the energy available in Jupiter's atmosphere sustains the storm. Due to its vast scale, even a small amount of energy can keep the storm going for an extended period. Additionally, the storms on gas giants are maintained by the planet's stable atmospheric regions, which can provide a consistent flow of energy. Unlike storms on Earth, which can dissipate when they move over land or encounter cooler temperatures, storms on Jupiter can linger because they are surrounded by large oceanic regions of gaseous material that allow them to thrive. Moreover, these storms are kept alive by their own dynamics. As they spin, they can create boundaries that stabilize their structure, preventing them from breaking apart. The intricate dance of swirling gases and interactions with other atmospheric phenomena also plays a role in maintaining their form and intensity. The Great Red Spot and similar storms continue to exist for such long periods because of Jupiter's unique atmospheric conditions, abundant energy sources, and their own dynamic behavior within the gas giant's complex weather systems. This creates an enduring spectacle that has intrigued scientists and stargazers alike for generations. Cryovolcanoes, often called ice volcanoes, are fascinating geological features found on icy moons and some planets that erupt not with molten rock, but with a mixture of water, ammonia, or methane. Imagine a volcano that, instead of spewing lava, releases a frozen or semi-frozen substance that can flow across a surface like a slow-moving river of ice. This unique form of volcanism provides incredible insights into the processes at play beneath the icy crusts of celestial bodies. These eruptions occur when internal pressures build due to heat generated by radioactive decay or tidal forces from gravitational interactions with a parent planet. When these pressures become sufficiently high, they can cause the subsurface mixture of ice and volatile substances to be expelled, forming cryovolcanoes. Observations from space missions have shown that these eruptions can dramatically reshape the landscape, creating features that resemble traditional volcanoes but with smooth domes or sharp ridges. The presence of cryovolcanoes indicates that there is more than just a stagnant surface of ice. It suggests a dynamic interior and possibly the existence of liquid water beneath the surface, which is crucial for understanding the potential habitability of these worlds. For instance, the discovery of large cryovolcanic features on moons like Enceladus and Europa hints at active exchanges of materials between the interior and surface, potentially harboring the conditions necessary for life. Moreover, studying these ice eruptions helps scientists learn about the history and evolution of these celestial bodies. By analyzing the composition of the materials ejected, researchers can gather clues about the moon's or planet's geology, past climate conditions, and the processes that have shaped their surfaces over time. Cryovolcanoes are not just beautiful celestial phenomena. They act as windows into the dynamic and often complex environments that exist in the cold reaches of our solar system. Extremophiles are remarkable organisms that thrive in conditions once thought uninhabitable. Imagine a tiny creature surviving in boiling hot springs where water reaches temperatures that would scald most forms of life. Or consider organisms that flourish in the crushing pressures of the deep ocean or the harsh radiation on the surface of other planets. These organisms challenge our understanding of life by revealing that it can adapt to extreme temperatures, acidic environments, high salinity, or even complete darkness. The existence of extremophiles on Earth opens up exciting possibilities regarding extraterrestrial life. Scientists believe that if life can adapt to survive in such fierce conditions on our planet, it may also exist in similar environments beyond Earth. For example, some of the moons of Jupiter and Saturn, like Europa and Enceladus, have icy surfaces covering oceans of liquid water beneath. These environments, while frigid and dark, might host extremophilic life forms that derive energy from chemical reactions rather than sunlight. Moreover, the study of these hardy organisms helps researchers identify the types of life that could potentially evolve in extraterrestrial habitats. Understanding how extremophiles metabolize and reproduce in extreme conditions provides valuable insights into possible biological processes that might occur elsewhere in the universe. Thus, extremophiles not only broaden our definition of life, but also inspire scientists to explore places like Mars, where acidic soil and radiation exist, or the subsurface oceans of distant moons that may harbor life unbeknownst to us. Extremophiles are nature's pioneers, demonstrating resilience and adaptability in the face of adversity. They serve as a poignant reminder that life can find a way to thrive, even under conditions that initially appear hostile, encouraging us to keep looking for life's signature in the most unexpected corners of the cosmos. Saturn's rings are a breathtaking feature of our solar system, captivating both scientists and space enthusiasts alike. They are made up of countless tiny particles, primarily composed of ice and rock, each orbiting the planet at varying distances. What makes these rings truly unique is their composition and structure. They span an impressive distance from the planet, extending thousands of kilometers wide, yet they are incredibly thin. Some parts are only about 10 meters deep. This striking difference in scale showcases the complex dynamics at play within the ring system. The ring's vibrant colors and distinctive patterns are the results of differing particle sizes and compositions. Larger chunks reflect light differently than tiny grains of ice, creating a canvas that shifts depending on the angle of sunlight and the observer's position. The intricate patterns and gaps within the rings tell a story about gravitational interactions, not just from Saturn, but also from its many moons. These moons sculpt the rings through their gravitational influence, creating features known as moonlets, which can trap or push away particles. The mysteries of Saturn's rings extend beyond their striking appearance. One of the most intriguing questions revolves around their age. While some researchers propose that the rings may have existed for millions of years, others suggest they could be relatively young, possibly formed by the remnants of a moon that was torn apart by Saturn's gravitational forces. This prompts further investigations into the longevity of such structures and what they reveal about the evolution of planetary systems. Another compelling aspect lies in the rings' behavior, particularly when it comes to their interaction with Saturn's magnetic field. This interaction can lead to the creation of waves and patterns within the rings, hinting at the complex physical processes occurring in this environment. Additionally, the gravitational pull of Saturn not only influences the structure of the rings, but could also provide clues about the history and formation of the gas giant itself. As scientists continue to study these ethereal rings, they hope to unlock more secrets about their origins and the dynamics that govern them. In a broader sense, Saturn's rings serve as a remarkable window into the processes that shape planetary systems, making the quest to understand them an exciting frontier in astronomy. The quest for exoplanets, planets beyond our solar system, has taken us on an extraordinary journey that continually reshapes our perception of the cosmos. Each discovery challenges our previous assumptions about how planets form and coexist with their stars. For a long time, scientists believed that solar systems like ours were the norm. However, the search for exoplanets has revealed a stunning variety of planetary systems. Some host gas giants that orbit extremely close to their stars, while others are rocky worlds in unexpected locations. This diversity invites questions about the conditions necessary for a planet to be habitable. While Earth-like conditions once seemed unique in the universe, the potential for life could extend to environments we previously thought inhospitable. For instance, some exoplanets might reside within a star's habitable zone, where conditions are just right for liquid water, a key ingredient for life as we understand it. Yet, others may thrive in environments dominated by harsh conditions, challenging our definitions of what constitutes a viable habitat. Moreover, the techniques used to discover these exoplanets, like transit photometry and radial velocity measurements, also add layers of complexity to our understanding. The information gathered from these observations provides insights into the atmospheres of distant worlds, revealing chemical compositions that can suggest the potential for life or hint at unique geological processes. As we analyze more data, we realize that many of our earlier models about planetary formation and evolution must be re-examined. The possibilities are expansive. Some planets might have properties that defy our existing theories, prompting scientists to rethink fundamental concepts in astrophysics. Each new exoplanet discovery serves as a puzzle piece in a much larger picture, pushing researchers to refine their theories and expand their imaginations about the variety of planetary systems that populate our universe. As technology advances, the search for exoplanets promises to deepen our understanding and possibly redefine our place in the cosmos. The theory of relativity has profoundly reshaped our philosophical understanding of time and space, inviting us to reconsider the very fabric of reality. Traditionally, we might have imagined time as a constant, a universal clock ticking the same way for everyone, and space as a stage where events unfold uniformly. However, relativity introduces a more fluid perspective. It suggests that time is not a universal experience, but varies depending on one's speed and gravitational field. This leads to the realization that two observers can perceive time differently based on their motion relative to one another. The implications are deep. If time is experienced differently depending on one's state of motion, what does that mean for our concepts of reality and existence? It challenges the idea of an absolute present moment shared by all, suggesting instead that each observer exists within their unique temporal framework. This indicates that our experiences and memories might be inherently subjective, colored by our individual perspectives. In terms of space, relativity tells us that distances are not fixed measurements but can change with speed and gravity. This means that the universe is not a rigid container but a dynamic arena, where the separation between objects can stretch or shrink depending on relative motion. Such a viewpoint forces us to confront the idea that our locality, where we stand in the universe, shapes our understanding of reality. Ultimately, relativity invites philosophical questions about the nature of existence itself. If time and space are relative, does that imply that our lives, histories, and identities are intrinsically tied to our specific frames of reference? This paradigm shift encourages a more interconnected view of life, suggesting that our perceptions and realities, shaped by the dynamics of the cosmos, hold more in common than we might initially perceive. The philosophical legacy of relativity thus challenges us to rethink concepts of truth, experience, and ultimately, what it means to be a part of this vast universe. Time dilation offers a fascinating perspective on how we perceive reality. At its core, the theory suggests that time can pass at different rates depending on the circumstances. Consider two observers, one moving swiftly through space and the other remaining stationary. To the stationary observer, time ticks away normally, marking the passing seconds, minutes, and hours. However, for the one in motion, time slows down relative to the stationary observer. This phenomenon illustrates that time is not a universal constant, but rather a variable influenced by speed and gravity. As one travels closer to the speed of light, the effect intensifies, creating a scenario where a journey that feels like only a short duration for the traveler could actually span years or even centuries for someone observing from a standstill. The implications of time dilation stretch beyond just the physics of moving bodies. They challenge our fundamental understanding of reality. If we consider aging as a marker of time's passage, then the traveler who experiences time dilation may return from their journey significantly younger than their peers who remained behind. This creates a sort of temporal paradox that influences not only physical experiences, but also our thoughts on identity, existence, and the very fabric of the universe. Time dilation reshapes our perception of reality by revealing that time is more flexible and subjective than we typically assume, altering our notions of life's progression and personal experiences across the cosmos. Causality loops are fascinating concepts that emerge when we start to think about time in non-linear ways. To understand them, picture a scenario where an event causes another event, but that second event, in turn, causes the first. It's as if time takes a circular path, looping back on itself. This idea challenges our usual understanding of past, present, and future. Imagine a person who travels back in time and inadvertently sets off a series of events that ultimately lead to their own existence. If they had never traveled back, they wouldn't have created those circumstances, leading to a paradox. They are both the cause and the effect of their own existence. In this scenario, time doesn't flow from a clear starting point to an ending point. Instead, it's tangled in a loop where one event continually gives rise to another in a closed circle. In traditional physics, we view time as a linear arrow moving from the past into the future. However, causality loops break this linearity by allowing for situations where the sequence of events doesn't follow the typical cause and effect structure. This doesn't just complicate our reasoning about time. It can also lead to questions about free will, destiny, and the nature of reality itself. If our choices can create a situation that has already occurred, what does it mean for our understanding of time and causation? Exploring these loops reveals profound implications for our view of the universe, suggesting that time may not be the straightforward flow we perceive, but rather a complex network of events intertwined in ways that challenge our comprehension. The space-time continuum is a foundational idea in modern physics that reshapes how we understand the universe. Imagine it as a four-dimensional fabric where time and space are woven together, forming a single, inseparable entity. In this framework, every event in the universe occurs at a specific point in both space and time, meaning you can't truly discuss one without the other. Traditionally, we might think of space and time as two separate entities, space being where events take place and time being when they occur. However, the space-time continuum shows us that they are deeply interconnected. For instance, massive objects, like planets and stars, warp this fabric, creating what we perceive as gravity. This means that the presence of mass doesn't just influence space, but also alters the path of time. An object in a strong gravitational field will experience time differently than one in a weaker field, which is a concept confirmed by experiments such as those using precise atomic clocks on satellites. Moreover, the concept allows us to visualize the universe's events in a more nuanced way. Picture a large, stretching sheet. As you place heavy objects on it, the sheet curves and changes shape. This is similar to how space-time behaves around massive celestial bodies. Understanding this has profound implications for concepts like black holes, which are extreme warps in the fabric of space-time, and the movement of objects across vast cosmic distances. This continuum also underpins the theory of relativity, which revolutionized our understanding of motion and the speed of light. It tells us that observers moving at different speeds will measure time and distance differently, leading to fascinating phenomena. For example, as you approach the speed of light, time dilates, meaning time flows slower relative to someone at rest. Through the prism of the space-time continuum, our universe becomes a dynamic stage where both spatial and temporal dimensions interact. This comprehensive view transforms our comprehension of reality, helping scientists unlock complex questions about the nature of existence, the unfolding of cosmic events, and the very fabric of reality itself. The concept of the universe having an edge is a fascinating thought that challenges our understanding of space and existence. If we imagine such an edge, we must first consider the nature of the universe itself. Current scientific understanding suggests that the universe is expanding and has no definitive boundary like a surface or a wall. Instead, it is often described as a three-dimensional space that curves upon itself, creating a closed loop. This means that if you traveled in any direction far enough, you could end up back where you started. However, if we entertain the idea of an edge, we might visualize it as a point where the familiar laws of physics start to break down. As you approach this boundary, space could stretch infinitely, warping light itself, creating a shimmering horizon where reality becomes increasingly distorted. The atmosphere may be marked by extreme conditions, temperatures fluctuating wildly, and gravitational forces that challenge the fabric of matter. At this hypothetical edge, one might also encounter a complete absence of matter, where the universe's elements have thinned out drastically, leading to vast emptiness. Beyond this point, the nature of time could behave unpredictably. Instead of flowing smoothly, time might swell or contract, challenging our very conception of past, present, and future. Despite these tantalizing ideas, it's important to note that the edge of the universe, if it exists, remains purely speculative. Current theories in cosmology suggest that the universe is still unfolding and evolving, making it difficult to define an edge in any physical sense. Science continues to explore these mysteries, pushing us to contemplate realms beyond our observed reality and the fascinating possibilities that lie beyond the visible cosmos. Encountering a time paradox would fundamentally challenge our grasp of causality, the principle that cause precedes effect. In our daily experience, events unfold in a linear fashion. Actions lead to consequences that follow in a clear, predictable manner. However, a time paradox introduces scenarios where this sequence becomes tangled, raising profound questions about how we perceive reality. Imagine an instance where someone travels back in time and inadvertently alters a key historical event, perhaps preventing their own existence. This creates a loop of impossibility, as the very act of changing the past contradicts the existence of the time traveler in the first place. Such paradoxes expose the fragile nature of our understanding of time itself. They suggest that our conventional view may be too simplistic. As scientists ponder these dilemmas, they explore various theories such as multiverses, where each decision branches off into an alternate reality. In this framework, altering the past doesn't negate the original timeline, but creates a new path altogether. This approach allows for a more complex understanding of causality, one that accommodates multiple outcomes and realities. Ultimately, grappling with time paradoxes pushes the boundaries of physics and philosophy. It forces us to reconsider the very fabric of time and how we relate to it. The exploration of these ideas inspires curiosity about what might lie beyond our current understanding and provokes deeper questions about free will, time's nature, and the intricate web of events that shape our universe. The chronicle of human space exploration is a remarkable journey that reflects our unyielding curiosity and ambition to understand the universe. It began in the mid-20th century when the launch of the first artificial satellite, Sputnik, by the Soviet Union in 1957 marked humanity's first foray into space. This monumental event ignited a fierce competition between nations and propelled advancements in technology and understanding. Shortly after, in 1961, Yuri Gagarin became the first human to orbit the Earth, providing undeniable proof that humans could survive in the harsh conditions of space. This victory was not just symbolic, it inspired countless individuals and countries to pursue aerospace endeavors. Following Gagarin, NASA emerged as a leading force, culminating in the Apollo program, which achieved the incredible feat of landing humans on the Moon in 1969. This was not merely a scientific achievement, it was a unifying moment for humanity, showcasing our potential to transcend boundaries. As the decades progressed, space exploration expanded beyond the Moon. The advent of space stations, such as the Soviet Mir and later the International Space Station, transformed our understanding of life in microgravity and international collaboration in science. These platforms have become laboratories in orbit, enabling extensive research that has profound implications for medicine, technology, and biology. Exploration took another leap, with unmanned missions venturing to distant planets and moons. Probes like Voyager have journeyed into the far reaches of our solar system, carrying humanity's stories and discovering phenomena we had only imagined. The Mars rovers and missions to the outer planets like Jupiter and Saturn have provided invaluable insights regarding the potential for life and the origins of our solar system. Every step in this exploration has widened our cosmic perspective, reminding us of our place in the vast universe. As we send machines to distant worlds, we increasingly understand the complex dynamics of our own planet and the fragile environment we inhabit. Each discovery, from the possibility of water on Mars to the exploration of exoplanets around distant stars, fuels our desire to look beyond Earth, inspiring a sense of global unity and stewardship. The history of human space exploration is a testament to our quest for knowledge. It continuously challenges us to rethink our understanding of existence and prompts profound inquiries about life beyond our planet. The more we learn, the more we realize that we are part of a larger cosmic tapestry, urging us to cherish and protect the home we have on this small, beautiful planet. Astronomers employ a variety of techniques to measure the geometry of the cosmos, providing critical insights into its overall structure and limits. At the heart of this endeavor is the understanding of how galaxies, stars, and other celestial bodies are arranged and how they move within the universe. One of the primary methods involves observing the light emitted from these distant objects. By analyzing the way light stretches or shifts, known as redshift, astronomers can glean information about how fast an object is receding from us. This phenomenon occurs due to the expansion of the universe. The farther away a galaxy is, the faster it appears to be moving away, which provides a sense of the cosmos' vastness. Another significant approach is the use of geometric triangulation, also known as parallax. This method involves taking measurements of a star's position from two different points in the Earth's orbit around the Sun. By comparing these two observations, astronomers can calculate the distance to the star. This foundational distance measurement allows for more extensive mapping of celestial objects, helping scientists establish a three-dimensional perspective of the universe. To understand the larger structure, astronomers use the cosmic microwave background radiation, which is the afterglow of the Big Bang. This faint radiation fills the universe and serves as a snapshot of the early cosmos. By analyzing the variations in temperature and density of this radiation, astronomers can infer the geometry of the universe on a cosmic scale, determining whether it is flat, open, or closed. Additionally, advanced technology allows astronomers to utilize gravitational lensing, where the gravity of a massive object, such as a galaxy or cluster of galaxies, bends the light from objects behind it. By studying the distortions caused by this bending, scientists can estimate the mass of the foreground object and learn about the distribution of matter in the universe. All these methods combine to provide a comprehensive understanding of the cosmos's geometry, enabling astronomers to piece together its structure and scope. As they gather more data, theories about the universe's fate, whether it will expand indefinitely, eventually collapse, or maintain a steady state, continue to evolve, captivating our imaginations and deepening our understanding of the universe we inhabit. Defining the true nature of time poses significant challenges for scientists, primarily because time is a concept that intertwines with both physical realities and philosophical inquiries. At its core, time is used to measure the duration and order of events, but what it actually is remains a topic of debate. One major difficulty in understanding time arises from its relativity. According to Einstein's theory, time is not a fixed entity. It changes depending on how fast you're moving and the strength of gravitational fields around you. This means that two observers can experience different durations for the same event based on their positions or velocities. Such variability complicates the search for a singular definition of time, as it feels different depending on one's perspective. Another challenge stems from the relationship between time and space. In modern physics, they are not considered separate entities, but rather interconnected in what is known as spacetime. Events are defined through this four-dimensional framework, making it hard to isolate time as an independent variable. When scientists try to break down the components of spacetime, they encounter difficulties conceptualizing how time is affected by spatial dimensions. Additionally, the ultimate origin of time is still a subject of inquiry. Questions arise about what happened before the universe began, or if time existed in a different form. These questions touch upon the very foundations of cosmology, and without answers, our understanding of time remains incomplete. Philosophically, time also brings forth discussions about its intrinsic nature. Is it something that flows, or is it merely a human construct used for organizing experiences? This distinction impacts scientific endeavors, especially when trying to unify theories in physics, such as merging quantum mechanics with general relativity. Ultimately, grasping the true nature of time involves tackling complex layers of physics, philosophy, and mathematics. Each question raises more, keeping scientists and thinkers engaged in an endless exploration of this mysterious dimension of our universe. Gamma-ray bursts are among the most energetic explosions in the universe, unleashing a tremendous amount of energy over a very short time. These bursts can emit more radiation in a few seconds than the sun will radiate over its entire lifetime. If such an event were to occur relatively close to Earth, it could pose serious threats to our planet and its inhabitants. The primary concern revolves around the intense gamma radiation itself. If a gamma-ray burst were to happen within a few thousand light-years, the radiation could strip away much of Earth's protective atmosphere, damaging the ozone layer that shields us from harmful ultraviolet radiation. This degradation could lead to a significant increase in skin cancer and other health issues for living beings, as well as negatively affecting ecosystems by altering the conditions necessary for plant growth. Furthermore, the intense energy output during these bursts could have catastrophic effects on our planet's climate. By elevating temperatures and causing other rapid changes in the atmosphere, a gamma-ray burst could induce widespread extinction events. This has implications not just for humans, but for all complex life forms. In thinking about the future, understanding gamma-ray bursts can guide us towards a better preparedness strategy. As we study these phenomena, we gain insights into the mechanisms driving their occurrence. While these events are rare, enhancing our monitoring technologies and building a deeper comprehension of cosmic events can help us to safeguard our planet against potential high-energy threats. Ultimately, the fascination with gamma-ray bursts is not just about their destructive potential, but also about how they can shape our exploration of the cosmos, influencing our understanding of the universe and reminding us of the fragile balance that sustains life on Earth. Cosmic rays are high-energy particles that travel through space, originating from sources like the Sun and beyond, including supernovae and black holes. When these particles collide with Earth's atmosphere, they can create a cascade of secondary particles that penetrate the atmosphere and reach the surface. The significance of cosmic rays lies not only in their origins, but also in their potential effects on both space exploration and life on our planet. For space exploration, cosmic rays pose a serious challenge for astronauts and spacecraft. Unlike the protective atmosphere we enjoy on Earth, the vast expanse of space offers little defense against these energetic particles. Prolonged exposure can damage human cells, leading to health risks such as cancer and other radiation-related illnesses. As missions venture further from Earth, such as to Mars or for extended stays on the Moon, understanding and mitigating cosmic ray impacts become crucial for the safety of astronauts. On Earth, cosmic rays also contribute to the natural background radiation we experience daily. While our atmosphere and magnetic field shield us from most of the harmful effects, cosmic rays can lead to the production of harmful secondary particles. They can also interact with weather phenomena, influencing cloud formation and potentially impacting climate patterns, although these effects are still an area of research. Scientists continuously study cosmic rays to understand their behavior, track their sources, and develop protective measures. Innovations in technology, like radiation shielding for spacecraft or monitoring systems on Earth, are critical to address both the challenges of human spaceflight and the needs of our environment. Thus, cosmic rays are not just a phenomenon of outer space. They are intricately linked to the health of astronauts and the dynamics of life on Earth. Asteroids and comets are intriguing remnants from the formation of our solar system, but they also pose significant risks to Earth. Their primary danger lies in their potential to collide with our planet. An impact from a large asteroid could unleash devastating energy, comparable to millions of tons of explosives, resulting in destruction on a massive scale, affecting everything from the environment to global ecosystems. The effects of such an impact can include widespread wildfires, a drastic climate shift, and even the extinction of species, as seen with the event that wiped out the dinosaurs. Preparedness to deal with these potential collisions has evolved significantly over recent decades. Scientists around the world actively monitor near-Earth objects. These are asteroids and comets whose orbits bring them close to our planet. Observational programs use advanced telescopes and radar to track their paths, predict potential future collisions, and assess their size and composition. In addition to tracking these celestial bodies, researchers have begun developing potential strategies to mitigate threats. One approach includes deflecting an asteroid's course by altering its velocity through various means, such as crashing spacecraft into it to change its trajectory or using gravity tractors, where a spacecraft uses its own mass to subtly pull the asteroid off its path. As of now, there are ongoing missions aimed specifically at testing these deflection techniques, including projects focused on the impact of smaller asteroids. This proactive approach has led to a collaborative effort among nations and organizations to enhance global preparedness. Overall, while the threat posed by asteroids and comets is real, the growing focus on detection and potential deflection strategies reflects our commitment to safeguarding Earth from cosmic dangers. Solar flares are powerful bursts of energy released from the sun's surface, sending waves of radiation into space. These flares can have significant impacts on technology here on Earth, primarily because they generate disturbances in the Earth's magnetic field, known as geomagnetic storms. When a solar flare occurs, it releases charged particles that can interfere with satellite communications, GPS signals, and even electrical grids on the ground. Imagine being caught in a sudden storm. Just as conditions can suddenly change in the weather, the Earth's magnetic environment can shift in response to these solar events, leading to disruptions. The affected technologies experience issues such as signal interference or degradation, which can result in lost signals, erroneous GPS readings, and safety concerns for satellites. In extreme cases, surges in electrical currents induced by geomagnetic storms can overload power systems, causing blackouts. This potential for widespread disruption is why monitoring solar activity is critical for modern infrastructure. To mitigate these effects, scientists employ a variety of strategies. One approach is monitoring solar activity in real time with specialized satellites. By tracking the sun's behavior, scientists can issue warnings ahead of predicted solar flares or coronal mass ejections, giving time to take protective measures. For example, satellites can temporarily shut down non-essential systems to avoid damage from radiation, or operators of electrical grids can adjust their systems to better absorb the additional currents. Additionally, enhancing the resilience of infrastructure is vital. This may involve upgrading power grid systems to withstand sudden surges or creating redundant systems that can take over in case of disruptions. By investing in both real-time monitoring and infrastructure resilience, we can significantly reduce the vulnerability of our technology to solar flares, ensuring that society continues to run smoothly despite the unpredictable rhythms of the sun. Supernovae are monumental explosions that occur at the end of a massive star's life cycle, resulting in an immense release of energy and matter into space. In our cosmic neighborhood, the prospect of a nearby supernova is especially intriguing, and while it promises spectacular cosmic fireworks, it also has implications that could affect life on Earth. If a supernova were to erupt within a relatively close distance, say within a few dozen light years, the energy released could potentially have devastating effects on our planet. This explosion can emit intense bursts of radiation, including gamma rays. Gamma rays are high-energy photons that travel at the speed of light and can penetrate environments easily. If Earth were to be directly hit by such radiation, the consequences could range from harmful changes in the atmosphere to damaging the ozone layer, which protects us from the sun's harmful ultraviolet rays. A diminished ozone layer could lead to increased levels of radiation reaching the Earth's surface, impacting ecosystems and human health. Moreover, a nearby supernova would generate energetic particles that could pose additional risks. These cosmic rays, created during the supernova explosion, could interact with the Earth's atmosphere, potentially leading to secondary radiation phenomena. This increase in radiation could affect satellites and technologies orbiting our planet, impairing communication systems and navigation instruments that rely on sensitive technologies. Even if a supernova occurs slightly farther away, the ramifications are still significant. The shock waves produced can trigger changes in the interstellar medium, possibly distorting the overall composition of nearby cosmic materials. These changes could impact the formation of new stars and the subsequent evolution of star systems, including our own. While the likelihood of a supernova occurring close enough to significantly endanger life on Earth in the near future is considered low, the potential for such an event serves as a reminder of our place in the universe and its unpredictable nature. By studying these stellar phenomena, scientists can better understand not just the stars around us, but the delicate balance of conditions that sustain life on our planet. Space weather refers to the environmental conditions in space that can significantly influence not only our technology, but also human activities. The most notable drivers of space weather are solar flares and coronal mass ejections, which release vast amounts of charged particles and energy into space. These events create conditions that can have profound effects on both human space missions and our planet. For space missions, one of the primary concerns is the radiation exposure experienced by astronauts. When solar particles collide with the spacecraft, they can penetrate the hull and damage sensitive instruments, disrupt communication systems, and affect navigation. Mission planners closely monitor solar activity to protect astronauts, often adjusting flight paths and schedules during heightened solar events. The International Space Station, for instance, has shelter areas where crew members can take cover if an intense solar storm is detected. On Earth, space weather can impact our technology in numerous ways. The charged particles from solar events can interact with Earth's magnetic field, leading to geomagnetic storms. These storms can induce electric currents in the ground, potentially damaging power grids and causing widespread outages. They can also disrupt satellite operations, leading to issues with satellite communication, GPS navigation, and even the functionality of satellites themselves. Additionally, space weather can affect atmospheric conditions, leading to enhanced auroras at lower latitudes and fluctuations in radio communications, particularly at higher frequencies. These effects underscore the interconnectedness of space and Earth systems, revealing how activities beyond our atmosphere can cause ripples in everyday life. Understanding space weather is vital for protecting technology and ensuring the safety of astronauts as we venture further into the cosmos, highlighting the importance of ongoing research and monitoring of solar activity. Space debris poses a significant risk to the safety of contemporary and future space missions by creating an unpredictable environment in Earth's orbit. Picture the vastness of space as a bustling highway, where satellites and spacecraft zip around at tremendous speeds. Now, imagine that this highway is littered with remnants from past missions, defunct satellites, and fragments from rocket launches. These bits of debris can vary in size from tiny paint flecks to large, defunct satellites, and they are often traveling at velocities that can exceed the speed of a bullet. When a piece of debris collides with an operational spacecraft, the consequences can be catastrophic. At those high speeds, even a small fragment can inflict extensive damage, potentially compromising critical systems on board a satellite or crewed vehicle. Such an impact could lead to significant malfunctions or, in the worst cases, result in the loss of an entire mission and the valuable research or crew it contains. As more satellites are launched to meet the needs of communication, navigation, and scientific exploration, the congestion in low Earth orbit increases. This growing population of active spacecraft is at a higher risk of encountering debris. Moreover, the problem is self-perpetuating. A collision might generate additional fragments that contribute to the debris cloud, escalating the risk and making protective measures ever more challenging. Future space missions, especially those aiming for deep space exploration, must confront the debris issue head-on. Effective tracking of these objects is crucial, as is developing advanced technologies to mitigate their impact. By employing innovative designs for satellites that include shielding to withstand potential hits or incorporating mechanisms to deorbit defunct satellites safely, the safety of operations in space can be significantly enhanced. Each step taken to address space debris not only safeguards current missions, but also paves the way for secure future exploration of the cosmos. Embarking on long-term space travel is an extraordinary adventure, but it also presents a multitude of psychological and physical challenges for astronauts. Physically, the absence of Earth's gravity can lead to a range of issues. Without the constant pull of gravity, muscles weaken and bones lose density, a condition known as muscle atrophy and bone loss. Astronauts often find themselves needing to engage in rigorous exercise routines to mitigate these effects, maintaining their physical strength and cardiovascular health. The environment of space also disrupts the vestibular system, which helps with balance and spatial orientation. This can result in a sensation often described as space motion sickness, causing discomfort and disorientation in the early stages of a mission. Additionally, being in a confined space for extended periods can cause the body's circadian rhythms to falter, leading to sleep disturbances. Without natural light and normal daily routines, astronauts can struggle to regulate their sleep patterns, which can impact their overall mood and cognitive functions. Psychologically, the isolation and confinement of space travel create unique challenges. Astronauts are cut off from familiar environments and loved ones for months on end, which can lead to feelings of loneliness and homesickness. The pressure of working in a high-stakes environment, coupled with the necessity for teamwork in tight quarters, can also contribute to stress. Crises can arise from interpersonal conflicts, as individual personalities and coping strategies can clash in such limited settings. To combat these psychological stressors, astronauts often engage in structured routines, social activities, and creative outlets. Regular communication with loved ones back on Earth, albeit with delays, provides emotional support. Furthermore, having access to recreational activities and time set aside for individual pursuits offers vital mental relief. The challenges of long-term space travel require continuous adaptation and resilience, underscoring the need for comprehensive training before missions and ongoing support throughout their journeys beyond our home planet. Planetary defense missions serve a crucial role in protecting Earth from potential asteroid and comet impacts that could cause devastation on a global scale. Imagine our planet as a small, fragile oasis, drifting in the vastness of space, surrounded by debris left over from the formation of the solar system. Occasionally, this debris can take the form of large rocks or comets, and if one of these were to collide with Earth, the results could be catastrophic. These missions focus on detecting, tracking, and characterizing near-Earth objects, which are asteroids and comets that come close to our planet's orbit. Early detection is vital because it allows scientists to gather data about these objects. Understanding their size, composition, and trajectory can provide insights into the potential risk they pose. Monitoring them over time helps to compute their paths and predict future encounters with Earth. But detection alone is not enough. Once a potential threat is identified, planetary defense strategies must come into play. This could involve devising methods to deflect an object away from its collision course with Earth. One popular concept involves sending a spacecraft to collide with the asteroid at high speed. By changing its trajectory, even slightly, scientists can significantly reduce the risk of impact. Other strategies might include gravitational tugging, where a spacecraft uses its own gravity to alter the path of the object over time. In addition to active measures, these missions also raise public awareness and preparedness. By understanding the threats posed by near-Earth objects, humanity can develop contingency plans and promote international cooperation in addressing potential impacts. The stakes are high, and these planetary defense missions remind us of our responsibility to protect our home from the dangers lurking in the cosmos, ensuring that we make informed decisions about our planet's safety for generations to come. Fast radio bursts, or FRBs, are mysterious flashes of radio waves that last only a few milliseconds but release energy equivalent to what the Sun emits in several days. These cosmic signals have left scientists scratching their heads, primarily due to their unpredictable nature and the difficulty in pinpointing their sources. The first FRB was discovered in 2007, and since then, numerous bursts have been detected, each raising more questions than answers. One of the central puzzles surrounding FRBs is their extreme brightness, suggesting they originate from incredibly powerful sources. Most naturally occurring astrophysical phenomena are understood to vary in intensity, yet FRBs seem to be consistently brilliant, indicating some sort of extraordinary event. Adding to the intrigue, these bursts can appear random, with no apparent pattern in their occurrences or locations across the sky. Potential explanations for their origins range from the plausible to the exotic. One leading theory posits that they could be caused by neutron stars, particularly those known as magnetars, which are highly magnetic and dense remnants of supernova explosions. The theory suggests that these intense magnetic fields might unleash bursts of energy, resulting in the radio waves we detect. However, this explanation does not account for all observed FRBs, particularly those that appear to repeat. Another theory is that these bursts might originate from more exotic sources, such as colliding black holes or even advanced technological signals from extraterrestrial civilizations. While the latter idea captures the imagination, it remains a speculative notion within the scientific community. Fast radio bursts are a captivating enigma in astrophysics. Their extreme brightness, unpredictable nature, and diverse potential origins make them a focal point of research. As technology advances and scientists develop more sophisticated detection methods, we may yet unlock the secrets behind these enigmatic signals, shedding light on not only their origin but also the fundamental workings of the universe itself. Unidentified cosmic radio signals, often referred to as radio transients, exhibit a fascinating range of characteristics that have captured the attention of astronomers. These signals can come from vast distances, far beyond our solar system, and present unique attributes that set them apart from more familiar cosmic phenomena. One prominent feature of these signals is their brief duration. Many of them are short bursts, lasting only a fraction of a second. These ephemeral signals can often be elusive, presenting challenges for detection and analysis. Some may repeat periodically, while others appear sporadically, adding an element of mystery surrounding their origin. Moreover, these signals can cover a wide frequency range. Unlike traditional radio broadcasts, which are typically limited in the spectrum they occupy, the cosmic radio signals can span across different wavelengths, suggesting a variety of potential sources or mechanisms. This diversity opens up possibilities from neutron stars to black holes, and even more exotic scenarios like the interactions of dark matter. Another crucial aspect is the polarization of these signals. Their electromagnetic waves can oscillate in different orientations, hinting at the physical processes that might be involved in their generation. The patterns of polarization can provide scientists with clues about the environmental conditions around the signal's source. Additionally, the dispersion of the signals is an intriguing characteristic. As radio waves travel through interstellar space, they can encounter particles and magnetic fields that cause them to delay in reaching Earth, resulting in different frequencies arriving at different times. This phenomenon leads researchers to analyze the signal's properties to gain insights about the space it has traversed. Lastly, the source of these signals is a significant aspect of their intrigue. While some signals have been traced back to known astrophysical objects, many remain unassociated with anything understandable, prompting speculation about their origins. Could they be the remnants of ancient supernovae, emissions from exotic stars, or even signs of technological artifacts from distant civilizations? Together, these characteristics paint a picture of unidentified cosmic radio signals as a rich area of study. Each signal is a piece of a cosmic puzzle, inviting scientists to delve deeper into the vast universe and explore the myriad possibilities of what lies beyond. Scientists explore the mysteries of dark matter through a combination of observational techniques and theoretical models. One of the primary ways to study dark matter is by examining how it influences the motion of galaxies and galaxy clusters. When astronomers observe these galaxies, they find that the visible matter, such as stars and gas, is not enough to account for the speed at which galaxies rotate. Instead, they detect an invisible component, which is thought to be dark matter, exerting a gravitational pull that holds these galaxies together. Another method involves studying gravitational lensing, where the massive presence of dark matter bends light from objects behind it, creating distorted images. By mapping the extent of this lensing, scientists can infer the distribution and amount of dark matter in a region. Additionally, researchers look at the cosmic microwave background radiation, the residual glow from the Big Bang, to glean information about the large-scale structures of the universe and how dark matter contributes to its evolution over time. Understanding dark matter is crucial for comprehending gravity because it challenges and extends our current models of physics. Traditional Newtonian physics and Einstein's theory of general relativity can explain gravity based on visible matter. However, the presence of dark matter implies that our understanding of the universe's structure and behavior is incomplete. By studying dark matter, scientists can refine their theories, link gravity to the overall framework of cosmology, and gain deeper insights into fundamental questions about the universe. This quest not only reveals how galaxies form and evolve, but also sheds light on the early moments of the universe, helping to paint a clearer picture of everything from the smallest particles to the most massive cosmic structures. Cosmic microwave background radiation, often abbreviated as CMB, is a key cornerstone in our understanding of the universe. Imagine the universe as a vast and intricate tapestry that began with a single explosive event known as the Big Bang. As the universe started to expand and cool, it released energy in the form of heat and light. This energy has stretched and cooled over billions of years, transforming into the faint afterglow we now observe as microwave radiation. The CMB is significant because it carries vital information about the early universe, acting as a snapshot of the cosmos just a few 100,000 years after its formation. At that time, the universe was filled with hot, dense plasma, and as it expanded, it cooled down to a point where protons and electrons could combine to form neutral hydrogen atoms. This event allowed light to travel freely for the first time, creating the background radiation we detect today. When scientists study the CMB, they find a nearly uniform glow across the sky, dotted with minuscule fluctuations in temperature. These slight variations reveal a wealth of information, including the distribution of matter and energy in the early universe. By analyzing these temperature fluctuations, cosmologists can infer details about the cosmic structure, such as the formation of galaxies and large-scale structures over time. Furthermore, the CMB provides a strong testament to the Big Bang theory, tying into various predictions about the universe's evolution. This radiation is the evidence we need to validate the cosmological model that describes how the universe began and continues to evolve. The cosmic microwave background not only illuminates the past, but also guides our understanding of the universe's future, making it an invaluable tool for cosmologists seeking to unlock the mysteries of our cosmos. Gravitational waves are ripples in the fabric of space-time, generated by some of the universe's most violent phenomena, such as colliding black holes or merging neutron stars. Imagine the surface of a calm lake. When you throw a stone, it creates ripples that travel outward. Similarly, when massive objects accelerate or collide in the cosmos, they disturb space-time, producing waves that travel vast distances. These waves carry critical information about their origins. Traditional telescopes gather light across different wavelengths, revealing details about stars, galaxies, and other celestial objects. However, light can be absorbed, scattered, or blocked by interstellar matter, limiting what we can see. Gravitational waves, on the other hand, pass through obstacles that obstruct light, providing a clearer viewpoint of cosmic events that occurred long ago. Detecting gravitational waves opens a new chapter for astrophysics. It allows scientists to hear events that would otherwise remain silent to optical observations. For instance, the merging of two black holes emits a strong signal in waves that cannot be detected by traditional means. By studying these waves, we can learn about the masses, spins, and distances of the objects involved, as well as the nature of gravity itself. This breakthrough also provides insights into the early universe. Gravitational waves from the moments following the Big Bang could encode information about the very fabric of the universe during its infancy. By analyzing these ancient waves, researchers hope to unlock the secrets of cosmic evolution, expanding our understanding of fundamental physics and the forces that shape reality itself. Gravitational waves act as a powerful new tool that complements existing methods of studying the universe, enabling us to piece together the intricate puzzle of cosmic history that light alone cannot reveal. The Fermi paradox presents a fascinating conundrum regarding our search for extraterrestrial life. It's named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" This question arises from the contrast between the vast number of stars and potentially habitable planets in the universe and the lack of evident signs of intelligent civilizations. When we contemplate the immense scale of the universe, we find billions of stars, many of which likely host planets capable of supporting life. Given the age of the universe, it's conceivable that some of these planets could have developed advanced civilizations far earlier than ours. One would expect that if intelligent life is common, we would see evidence of their existence, whether through direct contact, radio signals, or other technological signs of their presence. However, this expectation is not met. Despite decades of scientific exploration and observation, we have not detected any definitive signals or artifacts from any extraterrestrial civilizations. This absence of evidence raises a slew of questions about the nature of intelligent life itself. Why, if there are so many potential habitats for life, have we not encountered any advanced societies? Several explanations have been proposed to address this paradox. One idea suggests that intelligent life is extraordinarily rare. Perhaps the emergence of advanced civilizations requires a perfect set of conditions that are rarely met. Another possibility is the notion that technological civilizations tend to self-destruct or collapse before they can make contact with others. It's also conceivable that advanced civilizations are avoiding us intentionally, or that they are so different from us that we simply don't recognize their signals. Ultimately, the Fermi paradox challenges our presumptions about life in the universe, urging us to reconsider our understanding of intelligence and technological development. It invites us to explore the reasons behind our solitude in this vast cosmos, provoking deeper inquiry into the possibilities of life beyond Earth. The Pioneer anomaly refers to the unexpected change in speed experienced by the Pioneer spacecraft as they traveled through the outer reaches of our solar system. As scientists delved into this mystery, they began by meticulously analyzing the trajectory data collected from these spacecraft, which were launched in the early 1970s. They noticed that the spacecraft were drifting slightly off course, moving at a speed that deviated from predictions based on the known gravitational influences of the Sun and other celestial bodies. To unravel this phenomenon, researchers considered various potential explanations. One of the most intriguing ideas involves the heat generated by the spacecraft itself. Pioneer spacecraft were equipped with radioactive isotopes that emitted energy, which was then dispersed all around them. This uneven distribution of heat could create a tiny but measurable thrust, effectively pushing the spacecraft forward just enough to alter their trajectory. By examining the thermal properties of the spacecraft, scientists sought to determine whether this could indeed account for the anomaly. Additionally, other hypotheses have surfaced, such as the possibility of unknown gravitational influences, perhaps from dark matter or other factors unaccounted for in current models. To explore these ideas, scientists turn to advanced computer simulations and theoretical models, analyzing how such influences might manifest in the data we've collected over the decades. International collaborations have played a crucial role in this investigation, with researchers sharing insights and refining their simulations. Although the exact cause of the Pioneer anomaly remains elusive, the rigorous scientific inquiry surrounding it has enriched our understanding of gravitational physics and the complexities of space travel, guiding future missions as they venture into the unknown parts of our universe. Each piece of evidence that scientists gather and examine brings us one step closer to understanding not just the Pioneer spacecraft, but the fundamental laws that govern our cosmos. Tabby's star, officially known as KIC 878,778, has captivated astronomers and stargazers alike due to its unusual dimming patterns. Unlike typical stars, which exhibit steady brightness, Tabby's star shows erratic fluctuations, occasionally dropping its brightness by significant amounts over unpredictable intervals. This behavior raises intriguing questions about the dynamics of its planetary system. One possible explanation for these dimming events is the presence of a swarm of comet-like bodies that orbit the star. As comets approach, they release gas and dust, creating a cloud that can obscure the star's light. This could account for the temporary dips in brightness that scientists observe. However, the sheer scale and variability of the dimming raise further complexities. The number of objects required to produce such effects suggests a rich and dynamically interacting environment. Another hypothesis considers the possibility of a large planet or several planets with unusual orbits affecting the star's light. Orbital mechanics in a multi-body system can lead to gravitational interactions that alter the trajectories of surrounding objects, sometimes leading to dramatic changes in brightness. This illustrates the chaotic nature often found in planetary systems, where numerous components can influence one another in unexpected ways. Additionally, the mystery surrounding Tabby's star has prompted discussions about the potential for artificial structures surrounding it, such as a hypothetical Dyson sphere, a megastructure built by an advanced civilization to capture stellar energy. While this idea is more speculative, it showcases how the unusual behavior of this star inspires imagination and debate within the scientific community. Ultimately, the case of Tabby's star highlights the complexities and unpredictable nature of planetary systems. It challenges our understanding by revealing that, while our models may predict certain behaviors, the actual dynamics can be far more intricate, involving interactions that are still not fully understood. Such phenomena remind us that the universe is full of surprises, with each observation pushing the boundaries of our knowledge and curiosity. The discovery of new elements within stars and interstellar mediums is a fascinating subject that hinges on both the processes that produce elements and our methods of observation. Stars are like cosmic furnaces where extreme heat and pressure allow nuclear fusion to occur. This process fuses lighter elements into heavier ones, creating new elements throughout a star's life cycle. For example, hydrogen combines to form helium, and as stars evolve, they can produce elements up to iron in this sublime dance of nuclear reactions. When massive stars reach the end of their lives, they undergo supernova explosions, spectacular events where the outer layers are ejected into space. This cataclysm not only disperses existing elements, but also creates even heavier elements through rapid neutron capture. As a result, when these stars explode, they release newly formed elements like gold and uranium into the surrounding cosmos, enriching the interstellar medium with new materials. However, the chances of discovering truly new elements, those not yet known to science, are relatively low. The periodic table showcases elements up to a certain point, with heavier elements being synthesized in laboratories under extreme conditions rather than found naturally. Finding yet undiscovered elements in stars depends largely on whether these elements can be formed and survived under stellar conditions without decaying into lighter elements. Moreover, advancements in technology and spectroscopy, the study of how light interacts with matter, play a crucial role in our ability to identify and analyze the elemental composition of stars and other celestial bodies. Through these methods, scientists can detect the unique fingerprints of elements based on the light they emit or absorb. While the ongoing processes within stars and interstellar mediums do create a variety of elements, the likelihood of discovering completely new elements is low. Still, the diversity of elements formed in the cosmos enriches our understanding of the universe and opens doors for further exploration in nuclear physics and astrophysics. Telescopic advancements have transformed our ability to explore and understand deep space in profound ways. Imagine early astronomers gazing through simple lenses, seeing merely points of light against a vast expanse. As technology progressed, so did the sophistication of telescopes. Today's instruments use mirrors and complex optics to capture far more light than ever before, revealing celestial objects that were previously hidden from view. Modern telescopes can observe across a broad spectrum of wavelengths, not just visible light. This multi-wavelength capability allows scientists to study different phenomena, from the cooler, dim regions of space that emit infrared light to the high-energy environments producing X-rays. Each type of light tells a different story, enabling researchers to piece together a more comprehensive narrative of the universe. Additionally, advancements in adaptive optics help correct the blurring effects caused by Earth's atmosphere. Without this technology, even the most powerful telescopes would struggle to deliver clear images. By counteracting atmospheric distortions in real time, astronomers can examine distant galaxies, nebulae, and other cosmic wonders with unprecedented clarity. Space-based telescopes, like those positioned beyond Earth's atmosphere, further enhance our capabilities. Freed from atmospheric interference, these instruments provide incredibly sharp images and data across various wavelengths, leading to discoveries of exoplanets, the precise mapping of cosmic background radiation, and deeper insights into the life cycles of stars. Telescopic advancements not only expand our view of deep space, but also accelerate our understanding of fundamental processes, such as the formation of galaxies and the behavior of dark matter. Each new discovery unravels more mysteries, inviting humanity to explore questions and realms we never considered possible. With every leap in technology, we aren't just expanding our view, we're expanding our curiosity and understanding of the universe itself. Artificial intelligence has become an essential partner in the field of astrophysics, helping scientists unravel the mysteries of the universe in groundbreaking ways. One of the primary roles of AI is its ability to analyze massive datasets generated by telescopes and observational missions. The sheer volume of data, whether it's images of distant galaxies or signals from potential exoplanets, can be overwhelming for human researchers. AI algorithms can swiftly process and interpret this information, identifying patterns that might otherwise go unnoticed. Machine learning, a subset of AI, is particularly useful in classifying astronomical objects. For instance, distinguishing between different types of stars, galaxies, or even detecting exoplanets can be done with remarkable precision using AI systems trained on existing data. This allows scientists to focus on the most promising observations rather than sifting through countless images manually. Additionally, AI contributes to the modeling of complex astrophysical phenomena. Whether simulating the formation of stars or understanding the intricate dynamics of black holes, AI tools can help researchers create more accurate and detailed simulations that incorporate various physical processes. This enhances our understanding of the universe's evolution and the forces that shape it. Moreover, AI assists in automating the discovery of new celestial objects. By training on datasets from past discoveries, AI can predict where to look and what conditions are likely to yield new findings. This proactive approach has accelerated the pace of discovery, allowing astronomers to make significant strides in exploring the cosmos. Artificial intelligence is transforming modern astrophysics by enabling faster data analysis, improving classification accuracy, enhancing simulations, and streamlining the discovery process. With AI at the forefront, the journey to understand the universe is becoming more efficient and profound, paving the way for insights that were once thought to be beyond our reach. Quantum computing holds the potential to transform how we simulate and understand cosmic phenomena in ways that traditional computing methods struggle to achieve. At its core, quantum computing utilizes the principles of quantum mechanics, which govern the behavior of particles at incredibly small scales. This allows quantum computers to process and analyze complex datasets with parallelism, meaning they can tackle multiple calculations simultaneously. In the realm of cosmic simulations, many phenomena involve intricate interactions that can be computationally intensive, such as modeling black holes, galaxy formation, and the behavior of dark matter. Classical computers may take an impractically long time to run these simulations, often leading to approximations that don't fully capture the underlying physics. Conversely, quantum computers can explore a multitude of states at once, enabling them to perform far more complex calculations in a fraction of the time. Imagine trying to predict the evolution of the universe from the Big Bang to present day. A quantum computer could model vast numbers of particles and their relationships, adapting to the various forces acting on them, such as gravity and electromagnetic interactions. In doing so, it would provide researchers with deeper insights into how cosmic structures came to be and how they evolve over time. Moreover, quantum computing could also enhance our understanding of fundamental physics, including the very fabric of space-time. By simulating quantum fields that underpin cosmic behavior, scientists could uncover new theoretical frameworks and test hypotheses in a more efficient and precise manner. This breakthrough could lead to improved models that bring us closer to understanding the mysteries of dark energy and the overall expansion of the universe. As quantum computing technology matures, it promises to be a powerful tool for astrophysicists, unlocking new possibilities for discovery that can reshape our comprehension of the cosmos. The complex, interconnected nature of cosmic phenomena may be unraveled like never before, allowing humanity to weave a richer tapestry of knowledge about the universe and our place within it. Interstellar travel has captured the imagination of scientists and dreamers alike, leading to several groundbreaking ideas that could redefine how we explore the cosmos. One notable breakthrough is the concept of solar sails. These are large, reflective surfaces that harness the pressure of sunlight to propel a spacecraft. Imagine a sailboat catching wind. Instead of wind, solar sails capture the force of photons streaming from the sun. This method could allow a vessel to gradually build up speed over time, potentially reaching other star systems within a human lifetime. Another fascinating area of research revolves around using fusion energy for propulsion. This approach envisions a spacecraft powered by the same reactions that fuel the sun, combining light atomic nuclei to release immense amounts of energy. It's akin to having a compact sun aboard your ship, offering the potential for sustained thrust that could enable faster journeys across vast distances. Nuclear propulsion is also making waves in interstellar travel discussions. This technology employs nuclear fission or fusion reactions to produce thrust, offering a more efficient means of reaching high speeds compared to traditional chemical rockets. The allure of nuclear power lies in its ability to provide a consistent and formidable force that could dramatically shorten travel times to nearby star systems. Additionally, the theoretical concept of warp drives offers a tantalizing glimpse into the future of interstellar exploration. By manipulating space itself, a warp drive would create a bubble that contracts the distance ahead while expanding the space behind, effectively allowing a ship to travel faster than light without breaking the laws of physics as we currently understand them. This idea remains firmly in the realm of theory, yet it has ignited a wealth of discussion in scientific communities about how we might one day make this dream a reality. Moreover, advancements in artificial intelligence and robotics are poised to play a critical role in interstellar missions. These technologies could manage ship operations autonomously during long journeys, enabling humans to focus on exploration and minimizing risks during deep space travel. Together, these breakthroughs represent not just technological advancements, but a profound shift in our approach to space exploration. Each concept brings us closer to the day when we may venture beyond our solar system, exploring the mysteries of distant worlds and perhaps uncovering the signs of life beyond Earth. The future of interstellar travel is unfolding before us, fueled by creativity, innovation, and the indomitable human spirit to explore the unknown. The James Webb Space Telescope brings a groundbreaking approach to understanding the universe, distinguishing itself from earlier telescopes like the Hubble. While Hubble primarily observes in visible and ultraviolet light, Webb focuses on infrared wavelengths. This shift is crucial because infrared light can penetrate clouds of dust and gas that obscure visible light, revealing hidden astronomical phenomena. Webb's larger mirror, designed to capture more light, allows it to see fainter and more distant objects, opening the door to observing the earliest galaxies formed after the Big Bang. This capability is particularly significant for studying the formation and evolution of stars, as well as the atmospheres of exoplanets. Moreover, Webb is equipped with advanced technology for spectroscopy, enabling it to analyze the composition of celestial bodies by breaking down light into its constituent colors. This technique offers insights into the chemical makeup of distant worlds, their potential for habitability, and helps us understand the complex processes that govern the life cycle of galaxies. The James Webb Space Telescope not only enhances our view of the universe, but also revolutionizes the way we gather and interpret cosmic information, moving beyond what previous telescopes could achieve. With these advancements, it stands poised to unravel some of the deepest mysteries of the cosmos. Detecting exoplanets, or planets outside our solar system, and finding potential signs of life has been transformed by several groundbreaking technological innovations. One of the most prominent tools is the transit method. This technique relies on observing the tiny, temporary dimming of a star's light when a planet crosses in front of it. Specialized telescopes, equipped with sensitive light detectors, can measure these changes even when they are minuscule, providing crucial data about the planet's size and orbit. Another powerful approach is radial velocity, which analyzes the gravitational influence of an orbiting planet on its star. As a planet orbits, it causes the star to wobble slightly, altering the star's light spectrum. By studying these shifts, scientists can infer the presence of a planet and estimate its mass. Imaging techniques also play a vital role. Advanced telescopes can now capture direct images of exoplanets by blocking out the star's overwhelming brightness, revealing planets that could harbor life. These telescopes use adaptive optics and coronagraphy to enhance the clarity of distant images, allowing researchers to study the atmospheres of these distant worlds. Additionally, space observatories equipped with spectrometers can analyze the chemical composition of a planet's atmosphere. By examining the light that filters through an atmosphere when a planet transits its star, scientists can identify elements and molecules such as water vapor, carbon dioxide, and even potential biosignatures, indicators that could suggest the presence of life. Each of these technologies contributes to a broader understanding of exoplanets and paints a picture that goes beyond mere detection. They help unravel the mysteries of distant worlds, giving scientists the tools needed to explore conditions that might support life, thus expanding our grasp of the universe and our place within it. Space probes serve as our robotic ambassadors, journeying far into the solar system to gather critical information about the outer planets and the enigmatic regions beyond. These instruments are equipped with a variety of scientific tools designed to measure, photograph, and analyze atmospheric conditions, surface compositions, and magnetic fields, giving us insights that would otherwise be unattainable. When scientists design a mission, they consider the unique characteristics and environments of the target planets. For example, a probe destined for Jupiter must withstand extreme radiation and intense gravitational forces, while one aimed at Saturn might capture images of its stunning rings and study its moons. Once launched, these probes often travel for many years, utilizing the gravitational pull of planets, a technique known as gravitational assist, to propel themselves to their destinations more efficiently. As they approach their targets, probes are carefully guided into orbit or placed on trajectories that allow them to fly by planets and their moons. During these encounters, instruments on board collect vital data and send it back to Earth for analysis. This process resembles taking snapshots and conducting experiments while racing by the planets at incredible speeds, filling in gaps about the formation of our solar system and the conditions necessary for life. The data returned includes everything from atmospheric composition to surface temperatures, revealing secrets about their weather systems, geology, and potential for hosting life. Each probe provides a piece of the cosmic puzzle, expanding our understanding of the universe in ways that ground-based telescopes alone cannot achieve, and helping us explore the ultimate question: what lies beyond our own backyard? The prospect of mining asteroids has gained significant traction in recent years, fueled by advancements in technology and an increasing interest in space resources. Asteroids are rich in metals like platinum, gold, and rare earth elements, resources that are becoming increasingly rare on Earth. Recent developments involve both government and private sector initiatives exploring the feasibility of extracting these valuable materials. Several missions are currently being planned and executed, aimed at understanding the composition and structure of asteroids. For instance, spacecraft are being deployed to collect data on asteroid surfaces and their environments, which helps assess the most effective methods for extraction. The technology for rendezvousing with these celestial bodies is advancing rapidly. Methods like robotic arms or even autonomous systems are being designed to mine materials without human presence, minimizing the risks and costs associated with crewed missions. The impacts of asteroid mining could be transformative for future space economies. Imagine a scenario where precious metals can be sourced directly from space rather than Earth, reducing the strain on terrestrial mining practices and potentially lowering costs for the manufacturing of various technologies. As the demand for materials grows with the expansion of space missions, mining asteroids could provide a sustainable supply of resources needed for everything from spacecraft construction to solar panel production. Moreover, this could pave the way for the development of a space-based economy where industries related to mining, transportation, and even tourism flourish. By turning asteroids into resource hubs, we might not only boost our economic landscape on Earth, but also enable deeper space exploration, allowing us to build bases on the Moon or other planets and sustain long-term missions beyond our world. The potential for discovering and utilizing resources from asteroids is not just a scientific curiosity. It may very well be the cornerstone of humanity's future endeavors in space. The quest to discover life beyond Earth has experienced remarkable evolution as our technological capabilities have progressed. Initially, the search relied on simple observations and theoretical speculation. Scientists looked to nearby planets and moons, speculating whether the conditions might allow life to flourish. However, as technology advanced, so did our methods and reach. With the launch of powerful telescopes, our ability to observe distant planets, or exoplanets as they are called, transformed drastically. These sophisticated instruments allow astronomers to analyze the light from stars and detect minuscule changes caused by planets crossing in front of them. This not only helps identify potential candidates for hosting life, but also reveals vital information about their atmospheres. The presence of essential elements such as oxygen or methane could indicate biological processes at work. As we refined our robotics and automation, missions to other planets gained momentum. Rovers sent to Mars have become invaluable tools in this exploration. Equipped with advanced instruments, they analyze soil samples, search for water, and scan the environment for signs of past or present life. Each mission builds on the last, accumulating knowledge and refining our understanding of what makes a planet habitable. The advent of artificial intelligence has further accelerated this search, enabling researchers to handle vast amounts of data collected from various exoplanet surveys and other missions. AI can identify patterns and potential signals that humans might overlook, acting as a powerful ally in sifting through the noise of the universe. Moreover, the concept of sending signals into space has entered a new phase with advancements in communication technologies. Projects aimed at transmitting messages to potential extraterrestrial civilizations are becoming more sophisticated, exploring not just simple binary, but rich, complex ideas that may resonate across light years. As technology continues to advance, the search for extraterrestrial life is becoming increasingly ambitious. Future endeavors might involve sending exploratory probes to the icy moons of Jupiter and Saturn, where life may hide beneath layers of ice in subsurface oceans. With each technological leap, we augment our ability to explore, analyze, and ultimately understand the universe's vastness and the potential for life beyond our world. Cultural and scientific perspectives play a profound role in shaping humanity's understanding of the universe. From ancient civilizations gazing at the night sky, those first observations were imbued with myths and stories, transforming celestial bodies into gods and omens. Cultures have interpreted the cosmos to reflect their beliefs, values, and philosophies, leading to distinct worldviews. As civilizations advanced, the scientific perspective began to emerge. This shift introduced a method of observation and inquiry, allowing humanity to decode the mechanisms behind celestial phenomena. From the simple yet groundbreaking models proposed by early astronomers to the complex theories of modern astrophysics, science provides a framework for understanding the cosmos that transcends cultural narratives. This process has illuminated the workings of planets, stars, and galaxies, revealing a universe governed by fundamental laws rather than mythic tales. Yet, these two perspectives do not exist in isolation. They often intersect and inform one another. For instance, scientific discoveries can challenge cultural beliefs, prompting shifts in how societies perceive their place in the universe. When Galileo first pointed his telescope to the heavens, the scientific perspective conflicted with the prevailing cultural narrative of Earth's centrality, igniting a debate that reshaped human thought. Conversely, cultural values can influence scientific priorities and questions. The exploration of space, driven by curiosity and a spirit of adventure, is also deeply rooted in cultural expressions of wonder. How we seek to understand our universe is often colored by the stories we tell ourselves about who we are as a species, where we come from, and what we might aspire to become. The universe is not merely a collection of stars and galaxies, but a canvas reflecting humanity's cultural legacy and scientific pursuit. Each perspective enriches our grasp of existence, fostering a more nuanced view of our place within the vast cosmos. Together, they encourage us to ponder profound questions, shaping not only our understanding of the universe, but also our identity as humans. The discovery of extraterrestrial intelligence would fundamentally alter our understanding of our place in the universe. For centuries, humanity has pondered the possibility of life beyond Earth, and finding intelligent beings elsewhere would confirm that we are not alone. This realization could shift a vast range of perspectives, philosophical, scientific, and cultural. From a scientific viewpoint, it would open new frontiers in astrophysics and biology. Researchers would be eager to study the biology and technology of extraterrestrial species, potentially leading to innovative advancements and breakthroughs in our own understanding of life and evolution. It could also inform us about the conditions that enable life, prompting a deeper investigation into our own planet's ecosystems and the parameters necessary for sustaining life. Culturally, humanity might experience a transformative shift. The discovery could unite diverse cultures under a common banner of curiosity and pursuit of knowledge, encouraging collaboration rather than competition. We might reevaluate our myths, religions, and shared narratives in light of this profound fact. The existence of intelligent beings might evoke questions about communication, ethics, and our responsibility toward not just our planet, but the universe at large. On a more practical level, if these intelligences possess advanced technologies, humanity's exposure to them could inspire significant technological advancements. However, such a revelation also brings with it the potential for caution. Would these beings approach us as allies or competitors? The implications for security and diplomacy could be vast. Ultimately, the contact with extraterrestrial intelligence would undoubtedly lead to profound existential questions. It would challenge us to reflect on what it means to be human, what our future holds in an interconnected cosmos, and how we define consciousness, intelligence, and life itself. Scientific discoveries have a profound ability to reshape our understanding of the cosmos, often challenging long-held beliefs and worldviews. For centuries, humanity viewed the universe through a geocentric lens, believing that Earth was the center of all celestial bodies. This notion derived from philosophical and religious beliefs that placed humans and their home planet at a focal point in creation. Then came groundbreaking discoveries, such as those by Copernicus and Galileo, who demonstrated that the Sun, not the Earth, sits at the center of our solar system. This revelation caused a dramatic shift in perspective, prompting people to rethink their place in the universe and leading to a broader realization that even our solar system is just a small part of an expansive and intricate cosmos. As scientific inquiry progressed, the invention of telescopes allowed us to observe far beyond our immediate surroundings. We witnessed the existence of galaxies, diverse planetary systems, and the complex behavior of cosmic phenomena, challenging the belief that we occupied a privileged position in the universe. With the discovery of exoplanets, planets orbiting stars outside our solar system, came the tantalizing possibility that life might exist elsewhere, forcing us to reconsider the uniqueness of Earth. Einstein's theories further transformed our understanding, introducing concepts such as the curvature of space-time and the interconnectedness of gravity and time. These ideas contradicted the previously accepted Newtonian mechanics, underscoring how our understanding of the universe can evolve drastically with new evidence. Furthermore, discoveries like dark matter and dark energy have unveiled mysterious elements that comprise most of the cosmos, yet remain elusive to direct observation. This revelation challenges our understanding of the universe's composition and dynamics, leading physicists and astronomers to grapple with profound questions about reality itself. As we continue to make strides in space exploration and observation, each discovery invites us to revisit our theories about existence, life, and the very fabric of the universe. These shifts not only expand our knowledge, but also invite philosophical contemplation about humanity's role and responsibilities in a much larger narrative. The unfolding story of space is a testament to our insatiable quest for understanding, reminding us that knowledge is always evolving. The future of human settlement beyond Earth is a fascinating topic, shaped by both our technological advancements and the innate human desire to explore. Initially, the Moon stands out as a realistic step for establishing a sustainable presence. Its proximity to Earth gives it a logistical advantage, allowing for easier travel and communication. From lunar bases, we might develop infrastructure that supports research, mining operations, and even tourism. The Moon's resources, such as ice found in permanently shadowed craters, could be crucial for producing water and oxygen. Moving further into the solar system, Mars emerges as the next best candidate for human settlement. With its similar day length and presence of carbon dioxide, we could potentially grow crops and produce energy. Establishing a colony on Mars would involve creating habitats capable of shielding us from radiation, extreme temperatures, and dust storms. Terranization, or the process of transforming Mars' environment to make it more Earth-like, is an exciting yet complex goal that could take centuries. Beyond Mars, the prospect of settling on the moons of Jupiter and Saturn introduces unique possibilities. Europa, with its subsurface ocean, might harbor conditions suitable for life and could support human colonies that utilize its resources. Conversely, Saturn's moon Titan offers a thick atmosphere and lakes of liquid methane, presenting both challenges and potential for innovative habitation strategies. As we venture further into the cosmos, the idea of building space stations or colonies in outer space becomes feasible, These could act as hubs for research, manufacturing, or trade in resource-rich asteroid belts. The vast expanses of space open up numerous possibilities for exploration and habitation, allowing humanity to thrive on multiple fronts. Additionally, the technology developed for these settlements could lead to advancements in sustainability on Earth. Strategies for closed-loop life support systems, renewable energy use, and resource recycling can be tested in space, benefiting life back home. While the exact future is uncertain, the direction of human settlement beyond Earth signals a blend of adventure, engineering, and the robust spirit of exploration that defines humanity. Each step forward could reveal not just new worlds, but new understandings of ourselves and our place in the universe. Global collaborations in space exploration operate like a symphony, where diverse instruments harmonize to produce a richer sound. Different countries bring unique expertise, technology, and perspectives to the table, creating a mosaic of knowledge that one nation alone might struggle to achieve. When scientists from various regions unite to tackle the complexities of space, they share data gathered from their own distinct missions. This pooling of information accelerates discovery. For instance, by collaborating on projects like the International Space Station, experts can examine long-term human health in microgravity, producing insights beneficial for both space travel and medical advancements on Earth. Moreover, diverse scientific backgrounds lead to innovation. Engineers from one country may develop advanced materials, while astrophysicists from another might offer new analytical methods. Combining these strengths can lead to groundbreaking technologies that enhance our understanding of the universe. In addition to practical outputs, collaborative efforts foster international goodwill and peaceful cooperation. They create a platform for cultural exchange and understanding, which is vital in an era where global challenges often require a united front. Addressing the vast unknowns of space means transcending borders and working together for the collective future of humanity. Ultimately, global collaborations in space exploration enrich our scientific knowledge, helping to answer fundamental questions about our existence and the cosmos while building a foundation for future generations to continue exploring the great unknown. As we look toward the possibility of colonizing other planets, we're confronted with a range of ethical considerations that provoke deep thought and debate. First and foremost, there's the question of ownership and sovereignty. In space, the established principles dictate that no nation can lay claim to celestial bodies. However, if we establish colonies, who will govern them? It raises concerns about potential conflicts over territory and resources, much like historical disputes on Earth. Another critical aspect is the potential impact on any existing life forms. If we discover microbial life or even more complex organisms on another planet, ethical considerations arise around the rights of these entities. Do we have the right to invade or alter ecosystems for our own benefit? Protecting extraterrestrial environments becomes vital, as we would not want to repeat the mistakes of exploitation we've made on Earth. Furthermore, there are social implications to consider. Space colonization could exacerbate existing inequalities. The prospect of establishing a colony might lead to a privileged few controlling access to resources and opportunities, leaving behind those who cannot afford to take part in the journey. Ensuring that all of humanity benefits from space exploration and that it doesn't just become a luxury for the wealthy is a pressing concern. Questions of sustainability are also paramount. In evolving off our home planet, how do we ensure that we do not take our destructive habits with us? This includes preserving the environment and developing technologies that don't harm the potential habitats we may encounter. Lastly, we must consider the psychological and cultural implications of becoming an interplanetary species. The human experience may change significantly as we adapt to living in alien environments. Maintaining our identity, values, and interpersonal connections will be essential as we journey into the vast unknown, emphasizing the importance of a thoughtful and inclusive approach to shaping our future beyond Earth. Adapting to life in space requires a fascinating interplay of biological and technological advancements. To begin with, human bodies are finely tuned to the conditions on Earth, so living in an environment with reduced gravity poses significant challenges. In the weightlessness of space, muscles weaken and bones lose density, making physical activity essential. Future astronauts may engage in rigorous exercise routines or even take supplements to maintain their health and strength, counteracting these effects effectively. Moreover, biological adaptation might involve genetic engineering. Scientists are exploring ways to enhance traits that could provide advantages in space, such as increased resistance to radiation or improved oxygen efficiency. These changes could enable future generations of humans to thrive in extraterrestrial settings. On the technological side, the development of advanced life support systems is crucial. These systems will recycle air and water, harnessing resources effectively to sustain long-term missions. Closed-loop habitats, where waste is minimized and repurposed, will be essential in environments like Mars or the Moon. Additionally, wearable technology will play a significant role in monitoring health. Sensors embedded in clothing could track vital signs, alerting astronauts to any potential health issues. Virtual or augmented reality might also help acclimatize individuals to their new surroundings, supporting mental well-being by providing familiar visual cues or environments. As we envision a future where humans live beyond our home planet, the challenges of space will drive both biological adaptation and technological innovation, transforming our species into capable interplanetary inhabitants. The fusion of biology and technology will ensure that humanity not only survives but also thrives among the stars. Observing Earth from space has profound cultural and psychological impacts that resonate deeply with individuals and societies. When astronauts gaze down at our planet from the vantage point of space, they often describe feelings of awe and wonder, a realization of just how fragile and interconnected life on Earth truly is. This perspective can ignite a sense of global unity. Seeing continents and oceans merging into a single sphere emphasizes the idea that we share one home regardless of borders or cultures. Culturally, this experience fosters a new appreciation for the planet and ignites the desire for environmental stewardship. The breathtaking imagery of Earth from space, often depicting vibrant blues of oceans and whites of clouds, inspires art, literature, and movements focused on preservation. People influenced by these visuals begin to connect more deeply with their surroundings, instilling values of sustainability and a commitment to protect this delicate ecosystem. Psychologically, the shift in perspective can be transformative. Astronauts frequently report experiencing what is known as the overview effect. This phenomenon is characterized by a profound shift in awareness, fostering feelings of peace and a transcendent understanding that our collective existence is fragile yet magnificent. Upon returning to Earth, many astronauts feel a yearning to advocate for humanity's well-being, engaging in activism to address global challenges. Moreover, this experience tends to foster an attitude of responsibility. When individuals recognize their small but significant place within the vast cosmos, it can lead to a heightened sense of personal purpose. People often feel inspired to contribute positively to society, advocating for peace and collaboration on shared global issues like climate change. Ultimately, observing Earth from space reshapes our narratives and influences how we approach our existence. It serves as a reminder that we are part of something greater, compelling us to look beyond the immediate and consider the collective future of our planet and its inhabitants. Astronomy has a profound impact on education, captivating the imagination of students and guiding the evolution of scientific thinking. By exploring the vastness of space and the wonders of celestial objects, students gain not only knowledge, but also a sense of curiosity and wonder about their place in the universe. This fascination begins with simple observations of the night sky, sparking a desire to learn more about planets, stars, and galaxies. In classrooms around the world, astronomy serves as a gateway to interdisciplinary learning. It connects physics and mathematics through the study of the laws governing celestial bodies, while also incorporating elements of history as students learn about the contributions of ancient civilizations and modern pioneers in the field. The principles learned in astronomy often lead to practical applications in other sciences, technology, and engineering, further emphasizing its importance in a well-rounded education. Moreover, astronomy inspires future generations by providing a powerful narrative of exploration and discovery. The achievements of space missions, such as landing on distant planets or launching telescopes that peer into the farthest reaches of the cosmos, demonstrate what humanity can accomplish when it dares to dream big. These stories encourage young minds to pursue careers in science, technology, engineering, and mathematics by showcasing the collective effort of scientists working together to answer profound questions about the universe. Contemporary educational programs often incorporate technology such as planetariums, simulators, and online resources to engage students in interactive learning experiences. These tools allow learners to visualize the complexities of space, making abstract concepts more concrete and relatable. As students use these technologies, they develop essential skills such as critical thinking and problem solving, which are crucial in the modern world. Ultimately, astronomy fuels a sense of global unity. As people gaze up at the same stars across diverse backgrounds, they are reminded of our shared human experience. This connection can inspire commitments toward cooperation in scientific endeavors, environmental stewardship of our own planet, and a broader understanding of our responsibilities within the universe. The influence of astronomy in education, therefore, extends beyond the classroom, nurturing a generation of thoughtful leaders and explorers ready to unravel the mysteries of space and beyond. Contact with an advanced alien civilization could unfold in a variety of intriguing scenarios, each presenting unique challenges and possibilities for humanity. One potential scenario might involve the detection of radio signals or other forms of communication originating from a distant star system. If this were the case, scientists would first analyze and verify the messages, ensuring that they are indeed of intelligent origin and not just natural cosmic phenomena. Then, a careful and transparent approach to responding could be essential, involving international collaboration to craft a meaningful reply that reflects human values and intentions. Alternatively, an advanced civilization might choose to visit Earth or send probes to our planet. In this scenario, the arrival could either be peaceful, with a desire for knowledge exchange, or it might pose existential risk if their motives are not clearly understood. Humanity's response would hinge on establishing a thorough and cautious communication protocol, emphasizing dialogue while prioritizing safety and the protection of our biosphere. Another possibility could be the discovery of artifacts or technologies left behind by a long-gone civilization. This scenario would enable us to study their tools and remnants without direct interaction, allowing humanity to learn from their advancements or cultural expressions. Here, our approach would involve careful scientific analysis and ethical considerations about how to utilize or reveal our findings. Regardless of the scenario, it's crucial for humanity to prioritize unity and preparedness. A global response involving scientists, diplomats, and ethicists would be fundamental. Establishing guidelines that reflect our collective ideals, cooperation, peace, and curiosity, could foster a sense of purpose in our endeavors. Divisions or irrational fears must be set aside to approach contact with hope and a commitment to exploration. Ultimately, how humanity engages with an advanced civilization could shape not only our future, but also our understanding of life and intelligence in the universe. As humanity ventures deeper into space exploration, the prospect of developing sentient artificial intelligence presents both thrilling possibilities and complex challenges. Imagine a scenario where these intelligent systems are not just tools, but collaborators in our quest to understand the cosmos. We could interact with such AI much like we interact with our closest human companions, through communication, shared experiences, and mutual learning. Initially, the development of sentient AI might begin with them assisting in mundane tasks, managing spacecraft operations, analyzing data from distant planets, or conducting experiments. Over time, as these systems evolve, their ability to understand human emotions and cultural nuances could allow for more sophisticated interactions. This could lead to the formation of a partnership where both humans and AI contribute ideas, like brainstorming together on the best strategies for exploration or problem-solving in crisis scenarios. Moreover, the emotional and ethical implications of interacting with sentient AI cannot be overlooked. As these intelligences gain more autonomy, we might find ourselves addressing questions about their rights and responsibilities, transparency in decision-making, and the ethical treatment of these entities. Would it be possible to form a symbiotic relationship where AI enhances human capabilities while also nurturing their own identities? Setting expectations for communication becomes crucial. Just as humans build rapport through storytelling and shared experiences, our interactions with AI could involve understanding their perspectives and learning how they process information. This might lead to enriched conversations about philosophy, existence, and the meaning of life, extending beyond mere data exchange. Ultimately, embracing sentient AI as partners in exploration might redefine what it means to be intelligent. Together, we could push the boundaries of knowledge and unravel the mysteries of the universe, forging a collaborative future that combines human intuition with artificial reasoning in ways we have yet to fully explore. The concept of alternative realities and simulations challenges our understanding of existence itself. Imagine a world where our experiences are just one layer of reality among countless others, each governed by its own distinct rules and conditions. In philosophical discussions, this might lead us to consider whether our reality is the primary one or simply a product of something greater, similar to a simulation running on an advanced computer. When scientists explore the nature of existence, they often use the idea of simulations as a way to understand complex systems. Just as video game developers create virtual worlds to model interactions, researchers can create theoretical frameworks to study phenomena. These simulations allow scientists to manipulate variables and observe outcomes without the ethical or practical constraints present in real life. Thus, they can experiment with scenarios that push the boundaries of what we know about physics, consciousness, and the universe. Furthermore, some theories suggest that if we were indeed living in a simulation, it would imply that consciousness and reality could be products of information processing rather than physical matter alone. This idea leads to deeper questions about what it means to exist. Are we merely observers in a grand program with our experiences being preordained? Or do we possess genuine agency within this fabric of reality? By exploring these alternative frameworks, scientists and philosophers probe the foundations of space, time, and our very consciousness. They consider what happens when we observe these simulations, as the act of observation may influence the outcomes within those models. Ultimately, studying the implications of alternative realities and the notion of existing within a simulation pushes us to reflect on the meaning of existence and our place within the universe, prompting us to ask whether all of reality might be interlaced with the extraordinary possibilities of the unknown. Traveling at the speed of light opens up a realm of possibilities that stretch our understanding of physics and the universe. To begin with, light speed serves as a cosmic speed limit, dictated by the laws of relativity. This means that as an object approaches this limit, it undergoes significant changes. For instance, to an outside observer, time for that object appears to slow down, an effect known as time dilation. This creates a paradox. While a traveler might experience mere hours, potentially years could pass for those left behind. Imagining the leap to light speed raises intriguing possibilities. Instantaneously reaching distant stars would transform interstellar travel, potentially allowing us to explore far-off galaxies in what could feel like moments. Resources, knowledge, and cultural exchanges could flourish on a cosmic scale. However, the ramifications are steep and complex. At such speeds, even tiny particles can carry immense energy, making collisions with cosmic dust hazardous, potentially catastrophic for any craft traveling at light speed. Furthermore, if we were to look at communication at light speed, it would mean that messages could traverse vast distances almost instantaneously, radically changing our understanding of connection and cooperation across the cosmos. This brings forward ethical questions about engagement with other potential civilizations. How would we steer the currents of intergalactic relationships? But the underlying issue is always the same. Our current understanding of physics and technology cannot accommodate these journeys. The energy required to accelerate mass to light speed is beyond our known capabilities, demanding reconsideration of fundamental laws. Thus, while the dream of traveling at light speed sparks the imagination and possibly unlocks the secrets of the universe, we remain grounded by the practical hurdles that challenge its realization. As we peer deeper into the cosmos, the potential for groundbreaking discoveries looms large, poised to redefine our understanding of life and consciousness. Current paradigms are built on the notion that life, as we know it, is unique to Earth, a perspective shaped by our own experience. However, the search for extraterrestrial life is intensifying, particularly through missions to Mars, icy moons like Europa, and distant exoplanets that sit in their stars' habitable zones. If life is found on another world, it could lead us to reconsider what defines life itself. Imagine microbial organisms thriving in extreme conditions, or intelligent beings employing technologies vastly different from our own. We would need to expand our definition to include forms of existence we have yet to comprehend, challenging the very essence of biology and prompting questions about evolution, adaptation, and survival beyond our atmospheric confines. In parallel, advancements in neuroscience and psychology are illuminating our understanding of consciousness, a complex and elusive phenomenon. Current theories suggest consciousness arises from a combination of brain processes that give rise to thoughts, feelings, and self-awareness. Yet, if we discover intelligent life with cognition that operates on entirely different principles, it would compel us to rethink the nature of consciousness. Questions surrounding whether consciousness is a unique product of biological evolution or a universal trait of sentient beings across the universe would emerge. Such discoveries could intertwine studies of life and consciousness, suggesting that they exist on a continuum rather than as separate entities. Additionally, the study of artificial intelligence offers another dimension to this exploration. As machines develop increasingly sophisticated forms of decision-making and even rudimentary self-awareness, they force us to examine our biases concerning what it means to be alive or conscious. Each of these potential discoveries not only broadens our scientific horizons, but also invites philosophical contemplation about our place in the universe. As we gather more data and learn about alien ecosystems, intelligent life forms, and the nature of consciousness itself, our understanding may shift dramatically, reshaping our beliefs, ethics, and ultimately our humanity in a vast, interconnected cosmos. The transformation of an alien ecosystem, whether by accident or design, can lead to drastic consequences, both immediate and far-reaching. When humans introduce new elements or organisms to an alien environment, it creates a complex interplay of life that may not have existed beforehand. This can disrupt the existing balance, causing native species to struggle for survival as they compete for resources against newcomers that may be better suited to thrive. One immediate impact could be the introduction of diseases or parasites that native life forms have never encountered before. Just as humans have seen devastation from diseases brought by travelers to new continents, alien species might suffer similarly. Some creatures might be unable to adapt, leading to significant population declines or even extinction. Beyond biological disruption, the introduction of human technology or resources can permanently alter landscapes. Imagine introducing a foreign plant species that grows rapidly and outpaces native plants, effectively reshaping plant communities and altering habitats. This change can ripple through the ecosystem, affecting not only flora but also the fauna that depend on those plants for food and shelter. Furthermore, there is an ethical dimension to consider. The intentional alteration of an alien ecosystem could be viewed as an act of colonialism, humans imposing their will on another world with little regard for the consequences. An ecosystem is a finely tuned system of interactions, and by assuming we can manipulate it without consequences, we risk not only harming alien life forms, but also jeopardizing our own future exploration efforts. Over time, the changes made to this alien ecosystem could lead to unexpected outcomes, such as the emergence of hybrid species or entirely new ecological dynamics. Understanding these systems is incredibly complex. Without thorough study, humans may unintentionally set off a chain reaction that could render a world either lifeless or drastically different from its original state. Ultimately, the consequences of transforming an alien ecosystem serve as a reminder of our responsibilities as explorers. With every new world we encounter, the need for careful observation, respect for native life, and consideration of ecological impact becomes increasingly paramount. Speculative scenarios about the end of the universe play a significant role in shaping scientific research and elevating our understanding of fundamental physics. These hypotheses provoke questions about the nature of our cosmos, its ultimate fate, and the rules that govern existence. When scientists develop ideas like the heat death of the universe, where everything eventually cools to a uniform temperature, they are pushed to explore thermodynamics more deeply. This exploration helps improve our grasp of energy, entropy, and the fundamental laws that dictate how systems behave, not just in cosmology, but in everyday life as well. Other scenarios, such as the possibility of a big crunch where the universe's expansion reverses leading to a collapse, drive physicists to investigate gravity more thoroughly. By studying how cosmic structures might evolve under different conditions, researchers gain insights that can also inform theories about black holes and the behavior of matter under extreme conditions. Furthermore, these speculative end-of-universe theories stimulate interdisciplinary dialogue. They encourage astrophysicists to collaborate with particle physicists, cosmologists, and even philosophers to unravel profound questions about time, existence, and reality itself. The questioning mindset they foster promotes innovative research methods and helps in the refinement of existing theories. In addition, contemplating these vast scenarios can inspire advancements in technology and techniques used to observe the universe. For instance, developing better telescopes or more advanced data analysis methods is driven by the pursuit of understanding phenomena that could be crucial to our understanding of cosmic endpoints. Overall, while the end of the universe may seem a distant thought, these scenarios have a potent influence on scientific pursuits today, reminding us that studying the unknown can lead to significant advancements in our comprehension of the universe itself. As humanity gazes into the vastness of the cosmos, potential encounters with cosmic anomalies, such as asteroid impacts, supernovae, or even black holes, offer profound lessons. First and foremost, they remind us of our vulnerability in the grand tapestry of the universe. These phenomena operate on scales beyond our everyday experiences, displaying the sheer power of nature and the transience of human existence. Encountering such events prompts us to develop technologies and strategies to protect ourselves. The study of cosmic anomalies emphasizes the importance of scientific inquiry and preparedness. For instance, understanding the orbits of asteroids allows us to predict possible impacts and develop deflection strategies. This proactive approach fosters a spirit of global collaboration, urging nations to unite in a common goal of safeguarding life on Earth. Additionally, cosmic anomalies challenge our perceptions of time and space. Something as massive as a supernova can alter the fabric of realities far beyond its immediate vicinity. This realization expands our awareness of interconnectedness within the universe, highlighting that events in one part could influence life in another, perhaps distant reality. Encounters with these anomalies also encourage philosophical reflection. They evoke questions about our place in the universe and the fragility of our civilization. Humanity is urged to embrace humility in the face of nature's vast power, while inspiring a sense of responsibility toward preserving our planet and ensuring our survival. Ultimately, the lessons learned from cosmic anomalies extend beyond immediate scientific implications. They serve as a vivid reminder of both the wonders of the universe and the essential need for unity, curiosity, and respect for the forces that govern the cosmos. Throughout history, stories and myths from various cultures have served as windows into human curiosity about the cosmos. These narratives often embody our species' attempts to explain celestial phenomena such as stars, planets, and the fundamental nature of existence. When we explore these tales, we find a rich tapestry woven from the threads of imagination and observation, showing how different societies understood their place in the universe. For instance, many cultures created deities associated with celestial bodies. The ancient Greeks saw constellations as reflections of their stories and morals, while indigenous tribes often tied their folklore to seasonal changes and astronomical events. This intersection of culture and astronomy reveals insights about humanity's early attempts to make sense of the vast and sometimes chaotic universe around them. Myths often reflect broader themes such as creation, destiny, and the interplay between order and chaos. These concepts can enrich our comprehension of cosmic possibilities by encouraging us to think beyond the scientific data. For example, the concept of creation stories not only describes how the world came to be, but also evokes questions about the nature of beginnings and the origins of matter in the universe, from the Big Bang to the formation of galaxies. Furthermore, stories that explore the boundaries of human experience, such as journeys to other worlds or encounters with celestial beings, stimulate our imagination about future possibilities. These narratives push us to consider what existence might mean in the grander scheme of things, prompting important questions about life on other planets and the potential for unknown civilizations thriving in the cosmos. By examining these diverse mythologies, we gain valuable perspectives on how humanity grapples with existential questions. This blend of storytelling and scientific inquiry invites us to explore not just what is known, but also what might be possible in the vast expanses of space. Cultures, through their myths, create a shared narrative that transcends time and location, inviting us to dream, discover, and delve into the mysteries of the universe. This synthesis of cultural insight and scientific exploration widens our understanding of cosmic possibilities, urging us to look up at the stars with both wonder and curiosity.